Okay, welcome everyone to day 4 of ST4 2020. So we will start off today by Biswajit telling us about soft theorems. Over to you, Biswajit.
Okay, thank you. So last day we have discussed how to get classical soft theorem in four space-time dimension up to subleading order with some naive assumptions and some physical understandings. So the naive assumptions what we made is that even like what we have derived in the first two lectures, the soft graviton and the soft photon theorem in d greater than 4 are still valid in d equal to 4, or you can think that the d equal to 4 3-level soft theorem is also valid at loop level in d equal to 4. This is one of the assumptions, and then we consider the classical limit of the soft theorem and assume that that is also valid in d equal to 4. Then we have seen that the angular momentum dive, if we assume this thing and substitute the trajectories of the particle, we have seen that the angular momentum, classical angular momentum diverges. Then we give a prescription that if you replace the log sigma, sigma was basically the affine parameter for the trajectory of the particle, or the proper time you can think. So if you replace this log of mod sigma appearing in the classical angular momentum by log of omega inverse, thinking omega inverse is the cutoff for the sigma, then in this prescription we have shown how the subleading soft graviton theorem looks like. One can do the similar things for the soft photon theorem as well. And what we have, the assumption 2 basically comes from a physical understanding that if we are looking at gravitational or electromagnetic radiation of wavelength lambda omega inverse, then we should expect that the trajectories of the particle beyond the time scale after omega inverse, it should not affect the electromagnetic and gravitational radiation. So with these assumptions, we made a substitution rule, and then using these substitution rules, let me show how the soft photon factor looks like. So obviously the leading soft photon factor, whatever one has in higher dimension or even at 3-level in 4 space-time dimension, that would not been affected. Only the subleading order contribution will affect it, and in place of omega to the power 0 piece at the subleading order, now one have a log omega piece, and this is a new kind of non-analytic structure of the soft factor in when omega going to 0 limit. And what one find is that the structure, the factor is written here, and this what happens is that you can see the electromagnetic soft factor contains a sum over the particles b not equal to a, where eta a eta b equal to 1, and eta a is basically incoming if they are plus, or outgoing plus 1, or outgoing if they are minus 1. In a sense, you see that the sum basically runs over if both a and b particle, if the pair a and b both are outgoing, or the pair a and b both are incoming. So there is no relation between the incoming and the outgoing particle in the classical soft factor. And one of the thing, just I want to make sure that this is also like what you expect in a classical scattering process, because if so whatever the interpretation of this term is that if the particles are scattering and asymptotically they feel a long range interaction due to the other particles, and obviously in the asymptotic trajectory of the outgoing particles also can feel the long range interaction of the long range interaction of the outgoing particles, and the incoming particles feel the long range interaction of the incoming particles. Otherwise, if the incoming particles trajectory would be field long range interaction to outgoing particle, that like goes the violates the causality assumption. So this is what we have found is consistent with the causality. And also this log omega term is basically telling us that the asymptotic trajectories of the particles are basically not straight line, but they are still accelerating due to long range electromagnetic force by other particles, and that's why they radiate. And this radiation effect is taken care of by the subleading soft factor for the electromagnetic case. Okay, so now if we try to do the same thing for the subleading soft graviton factor, there we see that this effect is also already present, that the long range gravitational interaction due to long range gravitational interaction asymptotic trajectory of the particle contains the acceleration term, and that's why it will radiate. So that part is contained here. But with this, we have seen that there is some extra contributions, which is basically telling us that even like when the soft graviton is emitting, it also feels wrong in interaction due to the other particles present in the theory, and that basically we have shown gives a time delay effect, that if the from the scattering center to the detector the distance is r, it will take it will not take just the time to reach in the order of r, but it has a log r correction. And with this, we have added a term log omega to make it, in a sense, you can think of dimensionless, but also one has some physical understanding of why this log omega term is there from some independent calculations. And this basically tells us about the backscattering effect, in a sense, since the gravity wave is a wave, so it's backscattered with the background geometry produced by the other particles. So this basically is the information about the first line, the first log omega term. And you see this phase factor is multiplied to the leading Soft factor, and we expanded the exponential of this thing, keep only the second term. And that basically gives a also log omega contribution, and another log omega contribution is the usual origin, which we have also seen for the electromagnetic case. So this is how far we have seen. Then we asked the question, okay, like this is like with some naive assumptions we have gotten from classical limit of Soft theorem starting from higher dimensional one. But can we derive this thing from the scattering amplitude in 4 space-time dimensions? Then we discussed that actually the 4 space-time dimensions, the problem is that the S matrix is ill-defined because because if the massless particles runs in loop, there is IR divergence issue. So it's not clear that how to derive in terms of IR divergent S matrices. But you see, this is not a problem in usual, what people learn from usual quantum field theory course, because there one computes the inclusive cross section, and that is infrared finite, and people have the understanding that physical quantity should not be affected. But there what happens is that the loop if the massless particles runs in the loop, this has the IR divergent factor, and this cancels in the inclusive cross section when you take care of the if you put a IR cutoff for the loop momenta and you integrate out all the external photons which are radiating with energies below this IR cutoff, and then integrate out those in the inclusive cross section, then this precisely this photon which are emitting in the external state, which are energy below the resolution, that cancels the effect of the IR divergence which is coming from the loop in the inclusive cross section, and it makes the inclusive cross section IR finite. So you are safe. But since the Soft theorem relates to S matrices, so probably we have to make sense even in the S matrix level how to derive the Soft theorem in 4 space-time dimensions. So this was the question which we tried to pose. And we how we get rid of this thing is the strategy which I described, that we don't make each of the individual S matrices to be IR finite, but what we can do is that we can factor out the IR divergent piece from both the S matrices, and if it turns out to be both are same, we can probably cancel from each side, and we can make sense of Soft theorem in terms of the IR finite part of the S matrices. So in a sense, what we tell is that suppose this gamma n0, which is in high energy particles and no photon or graviton, this amplitude we can write in terms of a exponential times k for all, if we sum over all loop order, and then some regulated piece of the amplitude, and we demand that all the IR divergent piece is contained in this factor which factored out, and the regulated piece of this IR divergent piece, regulated piece of the amplitude is completely IR finite. So this is not a particular regularization parameter we will impose, but we will show that we will break the propagator in such a way, and computing the diagrams, one can, even for all loop momenta, one can expect this factorization property even without taking any soft limit or the loop restricting the loop momentum in any region. Similarly, if we can do for the n,1 amplitude, which contains one external photon or graviton, the same divergent piece, then probably comparing the infrared finite piece of the n+1 amplitude and the nth amplitude, probably we can get rid of the Soft factor. But this actually what I will explain is true for the electromagnetic case to derive Soft photon theorem, but if we try to derive the Soft graviton amplitude, we will see that this gamma n+1 contains some extra IR divergent piece which is not present in gamma n0. So that we have to IR regulate by putting some IR regulator and analyze separately. and that could also give some extra contribution to the log omega contribution at the subleading order. So that we have to take care carefully. Okay, so up to now, is there any question? Otherwise, I will proceed. Okay. So if there is no question, so let me proceed. So I have also explained a little bit about how to do this factorization of the IR divergent piece from the IR finite piece, but let me do once again. So what we have done is basically we basically break the, so I am now explaining only in case of say scalar QED. So I'm scalar quantum electrodynamics for simplicity. So break the photon propagator into two pieces, like the photon propagator was say d gamma of some L mu nu. So just which is in Feynman gauge looks like mu nu. We can break it into two pieces. One let us call, I'm changing a notation related to the last day, G mu nu AB. So I have put an index AB for the K and the G because these factors will depend on where the photon propagator is connected to which leg. So in a sense, obviously you can read that what will be this G mu nu AB, that will be nothing but eta mu nu minus K mu nu AB, right? Then only it will match to the first line. And let me give the expression for the K mu nu AB. So if the photon is connected to two scalar lines with momenta P and PB, then the expressions for K mu nu AB turns out to be L mu L nu epsilon. Okay, and this is the factor which we called yesterday as the B of PA, PB, and L. Okay, so how it helps, like why we have done these things. So I will explain why this L mu L nu factor and how to find this B factor, though I have given the result first. And the prescription is that what we want is that now if you suppose break this propagator into two parts, then you see one thing happens is that now if you have to suppose compute a diagram with one photon, this is a full photon, full virtual photon, then in place of this diagram now you have to compute two diagrams, one with a K photon plus one with G photon. And what we demand is that this diagram, if we compute with the K photon, this contains the full IR divergent piece. Okay, and if we compute any diagram with the G photon, that should be IR finite. This is one of the prescription for breaking it down. And with this, for simplicity, we also assume that if we compute a diagram with no external photons or anything, if the G photon is connected to directly to the momentum PA and directly to the momentum PB, then this vanishes. But obviously, like if the G photon is connected to not directly to the PA PB, suppose this is some K is inserting, then here it is PA plus K with the G photon, and here suppose it is still PB, this obviously not zero. So if the G photon is connected directly to the momentum P and PV, then this kind of diagram vanishes. So by using this condition, and also this will be IR divergent fully if you compute with the K photon and the G photon, one can fix the form of B which we have shown here. This is the form of B. One can fix this form of B. Okay, this is one of the detail. And the other thing is that why this L mu L nu factor in the B in the expression for the K mu nu, this L mu L nu factor, how it helps. So for that also we have given a motivation yesterday, is that how this L mu L nu helps in K mu nu expression. So suppose you see, suppose one scalar line is there and one K photon is connected. So K photon I am just putting with the arrow because you can think of this is a pure gauge thing. Like if you kind of compute a diagram replacing epsilon mu by L mu, this is what the notation usually Peskin uses. So this is L mu and this is PC plus L. So this amplitude, if you try to write it down, so this is completely, I think this is, let me call this is in an optional level. So this is kind of a 3-point correlation function of 2 scalar and 1 photon. So this is the structure PC square plus MC square. So this is one part is L mu part index is connected to the scalar line. The other new index part of the K photon propagator is connected to somewhere else. So you put maybe a cross. The vertex factor for the 2 scalar 1 photon, that you can write it down, 2 PC mu plus L mu, and there is another propagator with the momentum PC plus L whole square plus MC square. But one nice thing is that if you contact this L with this factor, you can see that this term, this full 3-point function can be written in terms of subtractions of 2 terms. MC square. So then you can now interpret how these 2 terms coming from. So if you interpret this thing, you can think that how this, what this corresponds to. This corresponds to if the photon is connected to the extreme right minus if the photon is connected to the extreme left. And this circle vertex are telling that there is no momentum factor in the vertex factor, only some charge QC is sitting there for the vertex. This is the circle vertex notation. And then here obviously PC plus L momentum is running if this is L, and if this is L and PC is running. So basically you can interpret this term to this diagram, interpret this term to this diagram. So what you can see is that if a K photon is attached to a scalar line, you can interpret this any like 3-point function appearing inside your amplitude, you can break into 2 parts like this. So this is yes.
This decomposition are you going to do in the loop momentum?
Yeah, the loop momentum. So this L, I will consider this to be some K photon loop momentum.
So when you integrate in the loop momentum,
right.
I mean in both the terms, meaning G mu nu and K mu nu that you had written down, in both the terms, the integration, the range of integration, will that be the same?
Yeah, the range of integration will be 0 to infinity.
Okay, so, and what is the claim that you will get this IR?
Yeah, the claim is that claim is that if I compute with the K photon propagator, what happens is that like the loop momentum is the full loop momentum, but now if you take the loop momentum small, you can see that diagram computed with the K photon propagator turns out to be contains the IR divergent piece. It becomes divergent. And the if you compute with the G photon propagator, then you can see that that is completely IR finite.
Okay.
Yeah, but this factorization is independent of like where you restricted your loop momenta or whether you have done soft expansion or not. Anything beyond, before doing anything, this is true in general.
Okay.
Sorry, why
Yes.
don't you have the denominator for the photon propagator?
Oh, just I have not
Yes,
written it down. Yeah, so there is denominator. So here
okay.
actually, so if I connect to some other line to this K photon propagator, then I have to write the denominator. So I'm just picking up the L mu piece of the K photon propagator. So what I am doing is that the K photon from the K photon propagator, I'm just picking the L mu part and just I am showing the effect of the L mu, what it is doing. The rest of the factor would have to, you have to multiply.
Okay, thanks.
Okay.
I have a question.
Quick question.
Yes. Sure.
This fact that you can decompose the propagator into two and you can take this a particular vertex and write it as a difference between two other vertices.
Right.
This is true in any interaction or only scalar QED?
Okay.
I mean,
So
is there any
first,
modification on this thing?
yeah, so the propagator choice what I have shown is true like for spinor Q, like it's independent of the external particle. You can, if you take spinor also, this also works for quantum electrodynamics. Now I will show that
Okay.
for QCD and gravity, people have also extended this analysis. Like for QCD, I think Ashok Sen in his debut paper, he has extended it. And for gravity, in our paper, we have generalized this technique to how to do KG decomposition in gravitational case. So now I think the existent set is basically quantum electrodynamics, QCD, and gravity.
Gravity, I see. And it's called KG decomposition.
Yeah, it's called actually Grammarian treatment because they are the first who derived this thing for QED case, spinor QED.
Okay.
So Grammarian technique, but since people call it K propagator, G propagator, even they have given the name. So that's why in literature people also call sometimes KG decomposition.
Okay, thanks.
Okay.
Vijay has a question.
Yeah, so when you like put the condition that G propagator is directly attached to PA or PB, it's a demand you are making, right?
Yes, this is the demand of simplicity we are making.
So is there any physical reason to make this?
No, there is no physical reason. So what happens is that if you don't make, so actually what I want to say is that, let me change the color. So what I want to say that if you don't demand, like to make this, that if you compute a diagram where G photon, if you connect G photon is IR finite and K photon is IR divergent, only this piece of the thing you can fix, this structure. What I am just putting by green color or the the line in the line.
Yeah.
So the curly line, so you will fix only these factors, but not the rest of the thing. And the rest of the thing actually gives you a IR finite answer. Okay, only the IR divergent piece, if you compare with the K photon, it is enough to the curly line part of the K mu nu. But what happens is that we have added this extra piece. What happens is that if you start with this thing, then you have to compute both kind of diagram. Like if suppose say there is one external photon is there, so then you have to compute this diagram, and this diagram. But what you see that then basically this also will be non-zero, but then some part of it cancels from this part if you don't choose this thing. But what I am, by choosing this thing, we see that it will simplify that we don't have to compute this kind of diagram because this G photon is connected to directly the P and PB momenta, so this will vanish. So this will help to simplify our calculations.
Okay. Yeah.
So we added some IR finite piece to the IR divergent piece to simplify our calculations. But if you choose differently, then you have to compute a lot of more diagram. But after the analysis, you will get the same result.
Okay.
Biswajit?
Yes.
I think Anish had asked this question yesterday, but I don't remember the answer now. So, is there a priori reason as to why this decomposition can isolate the IR divergence? Like, is there something like this can be done? Can something like this be done for UV divergences?
Okay. Yeah, I'm not sure whether this could be done for UV divergence, but I think UV divergence, what happens is that there one have the renormalization technique, and probably one can renormalize this thing, and all this thing will be fine. And also
Yeah.
this like the exponential factorization, whatever I am showing, this is in general, right? You can like, this is independent of UBIR, means I have not mentioned even the UBIR thing. This is in general for all loop momenta you can do this thing. Right?
What did you say? I didn't understand.
No, so I want to tell that this factorization property with the KG decomposition is true for all loop momenta. I have not specified that whether loop momentum have to be small or greater.
Right.
So for UV also you can do this thing in principle, because this runs for all loop momenta. So without even UV or IR limit, this could be done. Now you have to make sure that whether the G photon, like with the G photon, if you compute a UV like UV limit, if you take the loop momenta to be very large, then you have to make sure that whether the diagrams having G photon is UV divergent or not. That I have not checked yet. So maybe it's better to check that whether also this procedure also factor out in the K the UV divergent piece, and G may not have UV divergent piece. But I'm not sure that this happens, but I've not checked it also.
Okay.
This factorization is independent of whether you are taking the loop momentum small or greater. It's for all loop momenta. Then after that, you have to check that whether it helps to factor out the UV divergent piece.
But is there a priori reason as to why this can be done for IR divergences?
Is there a okay, means what I am telling is that so what I am telling is that if it is not even like means till now whatever I have described, it's not even needed the IR divergent issue. Like
Right, I understand, but at the end of the procedure, you will see that the IR divergences get like exponentiated like that, right?
Right.
So like the point is like you can do this for IR divergences. Like so, a priori like I mean, is it like something to do with masslessness, or like what is there some a priori reason why this can be done for IR divergences? Like maybe I'm not like not very clear about the question itself.
Yeah, I understand. Like, yeah, I don't know whether there is any a priori reason, but just we demanded that this whatever the factor out part that should be IR divergent, and the rest of the piece of the amplitude will be IR finite, and in that way it fixes this B function. But if you suppose demand that you want this K factor should contain the full UV divergent piece and the rest of the UV finite, whether one can do that and can cook up such kind of a B factor, I'm not sure.
I see. Okay, fine.
Yeah, maybe one can try and look.
Yeah.
Okay. So this not only like since we want to factor out the IR divergence piece for both endpoint amplitude and the n, 1 point amplitude. So we have to also show that for n, 1 point amplitude this also works. So for that you can show. So this involves a little computation, but I will show in only diagrammatically how this happens. Suppose you want to compute a two scalar, two photon correlation function. Then like suppose and you take suppose one of them to be some finite energy, or even you don't have to take, suppose one of the is the full photon which is with momentum K, and then one is basically a K photon is connected. So then it can connect in three ways. So you have to sum over three kind of diagrams. For scalar QED, there is a two scalar and two photon vertex is there. So this diagram is present. Otherwise for spinor, this diagram is not present. And then these three kind of diagrams you have to draw. This is the K photon. This is the K photon propagator. That's why I put a arrow, part of the K photon propagator, and this is also L mu momentum. This is L mu momentum. So now what you can see is that in this part of the and this part of this correlation function, you can apply the rule which you described here, right? And break it into two terms. Similarly, this part you can use the same relation and break into two parts. So let me then write it down. So this could be written as the circle vertex, this diagram, minus this diagram. second diagram as we are keeping it because there we have not make any such kind of, this will not simplify anything. So this is because the vertex already is there, and from this diagram you will get okay. And what you can see is that sum over this and this vanishes. So you will left with only this minus this diagram. Okay, so this is a crucial fact that this sum with this proper sign which is appears, these three diagrams vanishes and you will left with only these two diagrams. So what it is telling that even in presence of some external photon or in two loop diagrams, such that can be some other photon, that could be kg anything. So this kind of like breakdown will happen. And what it will do is that even in presence of some say external photon or anything, it will also move if you attach to a k photon propagator, it will break up into two parts where the k photon is connected to the extreme right or the extreme left with the circle vertex without the momentum factor. So how this helps now is that suppose you have a diagram like a loop diagram, and you see suppose this particle whatever you have, this is a on cell. Now we have done this is a off cell level correlation function level. Now suppose this propagator is on cell, then what you will do? So this is the momentum PC which was coming in. So then what we will do is that like in LSG reduction formula, you basically multiply by the inverse propagator, right? With this, if you take the on cell, the scalar particle is on cell, and then you put PC square plus MC square equal to 0. Then what's happened is that since this first diagram does not contains any propagator factor on over PC square M square, so if we multiply this thing, so by LSG reduction formula, then basically this vanishes in on cell for amplitude. The second diagram only remains, right? So it tells us that always like for a on cell amplitude, if you do this thing, then always you have to only consider if the k photon is connected to the extreme right. And then what I will show is that for all loop order, if you sum over this thing, it was how this amplitude basically exponent, how this IR divergence of the k photon propagator contribution basically exponentiate for both n and the n,1 amplitude, because you see this for n and n plus 1, both the cases basically it goes to the extreme right. And since this B factor which we have shown depends on only the momentum of the PA and PB, not whether it is connected to some external lines or not. So both have the same structure and it will exponentiate. So let me show in a minute.
So Biswajit?
Yes.
So in the previous slide, when you did the decomposition, finally the contribution is coming from the K photon. Is that right?
Yeah, here I am only taking the contribution of the K photon, but the G photon analysis I have not done.
No, I meant in the next slide. So when you had these three diagrams and decomposed into this as a difference of these two diagrams. So
right.
Finally the contribution, is it coming from the K photon part?
Yes, yes. So this L mu is basically K photon. So I am analyzing only the K photon piece. One have to do the same analysis for the G photon, and there it will not happen such kind of things. There one have to compute the whole diagrams with the G photon. So this is I am only if we attach a K photon, I want to see what is the effect. The G photon part is still left as it is, and I will show that one have to explicitly compute.
Okay.
So if you attach a K photon, I will show that it exponentiates and it will cancel from both sides. Then all the diagrams what you have in your mind, you have to compute all this diagram with the G photon. Because the K photon part, it will exponentiate and cancels from both sides. So for that, let me first do that. What happens for gamma n0? So for the gamma n0 case, suppose look for suppose a one loop diagram. Okay. So some happening and some A and B particle, P and PB momentum, those are coming in, and some loop momentum is going here. Okay, so this momentum is PA. One have to sum over all these one loop diagrams, so sum over all A and B. Okay, then this contains a PA minus small l. This will have a PB plus small l, the factor. And this is completely on cell amplitude. So I will use P square plus M square equal to 0, PV square plus MB square equal to 0. And then this diagram is basically all sum over all the diagrams which are basically the tree diagrams. So I will call this gamma n comma 0 tree. Okay. Then what you can show is that due to this factorization property, if you now suppose like this is the diagram. So this diagram, if you compute, then basically it turns out to be K electromagnetic times gamma n comma 0 tree. Without any whether loop momentum is small or greater anything for all loop momenta, where I am writing the expression for the K electromagnetic, which is I by 2. You have to sum over all AB pairs not equal to B. Like if you can see that if you include A equal to B, that will give a self energy kind of diagrams, and those basically like can give your mass normalization and the wave function normalization. Mass normalization will tell you that you have to use basically like the renormalized mass in the propagator, and the wave function normalization is anyway cancels from both gamma n comma 0 and gamma n comma 1 piece, because both have n number of scalars there, so that will not affect. So that's why I am not drawing any kind of like the diagrams where the photon propagator is connected to the both the ends are connected to the 8th line or bth line. So and the B factor whatever you have. This is the B factor whatever you have in the K moment. When you see that now if you take the loop momentum L is tends to 0 or less than the finite energy particles, then this basically goes like d4 L upon L to the power 4, and this is divergent, right? Because you see that there is a L squared in the denominator. When L is small compared to P, this is the dominating term, this is the dominating term, and this gives 1 over L, and these are the numerator factor dominating term. So 4 powers in the numerator from d4L and 4 powers in the denominator from these 4 factors. And this is IR divergent when basically if you put some IR cutoff, say R inverse, then if you take this thing to be 0, R inverse to be 0, then this is completely IR divergent, logarithm again. Okay. So this is one loop, but how really, if you sum over all loop diagrams, how this goes. So here what we have done is that we have computed this diagram with only K photon. So this is a K photon. Now you have to actually sum over all, like suppose up to one loop, you are summing over the diagrams up to one loop. You want to find what is gamma n0. Then you have to do is basically you have to sum the tree part of the gamma n0 plus gamma n0 with the K photon piece at one loop, and plus gamma n0 with the G photon piece at one loop, computed with the G photon propagator, right? And what we have shown that if you compute with the K photon, that basically becomes K electromagnetic times gamma n comma 0 tree. So what you get is basically 1 plus K electromagnetic gamma n comma 0 tree, plus you have to compute the n comma 0 one loop diagram with the G photon at one loop level. Now you do the similar analysis, now go to 2 loop and higher loops, and suppose you go to n loop which contains the ng number of G photon and n k number of K photon propagators, and you have a symmetry factor over 1 by ng factorial 1 by nk factorial, and you sum over all possibles nj and nk, which is sum give you n gamma n loop, and then you sum over all the n's. Finally what you will find is that doing this thing, you can show that all loop amplitude, if you compute gamma n0, that basically gives you exponential of K electromagnetic times gamma n comma 0 G, while this factor is telling us that you have to compute all the loop diagrams replacing all the photon propagator with the G photon propagator. So this contains say gamma n comma 0 3 plus gamma n comma 0 1 loop with G photon plus 2 loop with G photon, 3 loop with G photon all. So all the diagrams, whatever you have mind for n number of scalar particles, we just replace all the photon propagator by G photon propagator, and that will be this gamma n comma 0 G, which we earlier called the regulated piece or the IR finite piece of the n comma 0 amplitude. So up to now, is there any question?
Biswajit, can you just repeat the last thing, the exponentiation argument
Okay,
for G, gamma G?
Okay, so what I have shown is that, like, if you expand, suppose this thing, if you use this relation up to 1 loop order, so what you can see is that this exponential give 1 plus k electromagnetic times say 3 plus, so let me, so okay, maybe I should go. So what happens is that, suppose you want to compute up to n loop diagram, okay, up to n loop.
Okay.
So basically, then what will be your amplitude? Like you will show that you have to basically suppose n0, the n loop. That basically you have to do is basically, I'm explaining what are the different factors are. Factors, and then basically you will have a electromagnetic times nk, and then yeah, you have to sum over all the diagrams. So I think ng, and then sorry, I think I'm just writing this thing. So then you have to compute a n comma 0 amplitude of n loop, but which has ng number of G photon propagator and nk number of k photon propagator, right? And then you have to sum over all ng and nk, but you have to restrict that ng plus nk should be n. Okay.
Right.
And then what you can show that this amplitude, if you have a nk number of k photon, then you can write it in terms of like k electromagnetic times nk number of k photon factor, and then the rest of the amplitude you have to compute only with ng number of G photon propagator.
Right.
Okay. And then if you make this sum, and then what you will find finally is basically, and these factors are symmetry factors because you know, like the loop momentums are basically identical photons because all the loop momentum integration is done. So this is why the symmetry factor is. And then basically you will show that this one can show k electromagnetic times you have to sum over all loop. Now this is one loop. Now you have to sum over this thing for this n loop to be n equal to 0 to infinity, right?
Okay.
After doing this thing. And then what you will able to show that then basically you have to compute all the loop diagrams with the G photon propagator from tree to loop. In that way you will get. So this is just a little sketchy thing which I explained, but if you see this paper of grammar any.
I see. So what was a bit confusing for me was the fact that they split nicely. I mean, in the intermediate, the summation is over both nk and ng.
Right, but it is restricted to nk plus ng equal to n. Now what happens is that if you take this n to be infinity, then this restriction will go out. Then ng can be arbitrary and nk can be also be arbitrary.
I see.
When you come here actually.
I see.
Means there is a detailed intermediate steps, but which I forgot long time back I read, but this is the logic.
Okay.
Follow. Okay. So then you have to, if this happens, now you see that what we have explained is that the same kind of things happens even if in presence of there is some external photon is there. Say for example, so since this factorization also happens if there is some external photon is there, So even for n plus 1, the same thing will go, because of this factorization is similar to the gamma n comma 0. So in a similar way, you can also prove that gamma n comma 1 up to all loop order, this is the full amplitude, also has the same exponential factor times gamma n comma 0 all loop. All loop means it contains also the tree. So then if it happens, then like for QED case, this actually happens. I will show how to do the stability for gravity. And if this happens, then you cancel. And since you know that you will expect the subletting soft factor is a multiplicative soft factor, because you know the classical thing, it is a multiplicative soft factor. So if you also start with a infrared divergent piece of the amplitude, considering some S0 plus S1, which will be the full amplitude comma n
Sorry,
comma 0. Yes.
On the top right hand side, it will be gamma n comma 0 or n comma 1 all loop.
Oh, sorry, n comma 1. Thank you.
So one question here, like this on the right hand side, gamma n comma 1, that is the
This is the with the G with sorry
with the G,
with the G
I'm just
photon.
trying to understand, like so this is the tree level, right? I mean, for example, if you're just say for one loop, let's say n comma 1 loop, on the right hand side you will get an exponential factor times gamma n comma 1
tree level only.
Yeah, tree level only. Right. And that tree level will also have this soft photon attached, which will give a factor of 1 by omega.
Right. So that I will show how cancels from both sides.
No, I'm just asking that this 1 over omega, you are not considering that as IR divergence. Is that right?
Right.
It's a soft divergence.
Yeah, this is the extra, like this is not a, like IR divergence, I'll consider only if it is coming from the loop. Okay. So if there is some soft divergence, 1 over omega is a soft divergence, that will keep as it is.
Okay, fine, thanks.
Okay. So then after cancelling this thing, you will, if S1 is a multiplicative operator, this is what from the classical thing we have shown that if log omega term is a multiplicative operator, not a differential. So if we expect the quantum term also is a multiplicative term, then you can remove the exponential k from both the sides, and you can say that okay, n comma 1 with the G photon should be same comma 0 with the G photon. Now you see that suppose you are analyzing up to one loop. So this will go like if you not only try to derive the subleading order, but sub-subleading all orders, because this G and the diagrams computed up to the G photon is all loop order result. So you can extend this to 2 loop, 3 loop results also and try to extract beyond log omega corrections. But now if you restrict to one loop, what happens is that this is basically now is 3 n comma 1 plus gamma n comma 1 with the G photon one loop. And this, you know that gamma n comma 1 tree is basically S0 times gamma n comma 0 tree, right? And here, then this also contains gamma n comma 0 tree plus gamma n comma 0 one loop with the G photon one loop. But we have seen that this diagram is vanishing by our simplification choice that we made. That if you compute a endpoint amplitude with one G photon propagator, that vanishes. This is a simplicity assumptions we have done, so we can throw this piece. Okay, and now you see that the 3 part, if it is multiplied to the S0, that also cancels with this term, right? Because it is also S0 times gamma n0 t, and this is S0 times gamma n0 t. So only you are left with this S1 times gamma n0 t, which is basically you can get if you compute a one loop diagram with the G photon with the n plus n0, 1 amplitude. So what you will finally get in this analysis is that the algorithm to find S1, which is the logarithmic soft factor, is basically you have to compute n comma 1 amplitude up to 1 loop with the G photon. That will give the soft factor times the gamma n comma 0 tree, which we consider, suppose so this is what one have to do. So you have to divide by this gamma n comma 0 tree factor to get rid of what will be the subleading soft factor. This is the logarithmic subleading soft factor. Okay. So now basically, then what you have to do, you have to compute this side. This is what you have to do, and then you have to take a soft limit to extract the S1. So only here up to after this, all these things, now the soft limit comes in. So what kind of diagram you have to compute? So in scalar QED, it is very simple to guess what are the one loop diagrams which have n plus 1 amplitude. So let me focus on, say, for simplicity, 4 scalar interaction, like a theory which has a 4 scalar interaction, phi star phi square times I lambda kind of interaction. And it is a scalar QED theory. But like this can be done for any endpoint interactions, but just simplicity I am showing here. So roughly you have to, leaving the self energy diagrams, which you already explained that you don't have to compute for the QED case. So you have to basically compute these 3 kind of diagrams with all the photon propagator. Now you have the G photon propagator. And so this is some eighth particle, this is with particle, eighth particle with particle, eighth particle with particle, and you have to sum over all these A and B. If there is n number of scattering or n number of particles are scattering, then you have to sum over all of this pair over n number of variables. But as you see that since this G photon is exposed to the momentum PA and PB, so in the same logic what we have done for gamma n comma 0, if you compute with the G photon, this logic also goes here and this amplitude vanishes. This is why we have done these simplicity assumptions, and basically roughly it turns out that we have to compute only these 2 diagrams. And by like constructions, already we know that if you compute these 2 diagrams, if you take the loop momentum smaller than all the scales, like loop momentum going to 0, those that don't have IR divergent piece. So these are completely IR finite. Then you will expect from where you will get a logarithmic omega term. So if you analyze this diagram with say loop moment, so this is suppose external photon with momentum k, this is a loop momentum L. What you will see is that when the loop momenta component, each of the loop momenta component is much greater than omega. Omega is the energy of this external photon, so omega n mu, and smaller than the finite energy particles momenta, then these diagrams basically gives you a logarithmic kind of integral, and the lower limit of the integral is omega, so that will contribute to log omega. Okay.
Biswajit,
So, yes.
Why aren't there like self energy diagrams for the G photon?
Yeah, so like you will expect that. So if you analyze, say, why not this kind of diagram if this is a G photon propagator, right?
Yeah. I mean, for scalar QED, I don't think that is possible, but
yeah. So I think this kind of diagrams are also possible, but you can show that if you analyze this kind of diagram, those don't contribute to log omega term. So that's why I'm not throwing in. I mean, I'm just throwing this.
Oh, it's not 0, but it does not give you a logarithmic divergence.
Yeah. So these diagrams, and okay, I think for scalar QED, it's not obviously 0 because it has like it has obviously UV divergent piece with you will renormalize your 3-point function to scalar 1 photon 3-point functions, right? So it is not in general 0, but the IR, like if you analyze that all the integration regions, you can see that that does not contribute to log omega.
Okay.
Yeah.
So Biswajit, if you had gone to higher loop orders, so then also can you say that not log omega, but say let's say log omega square or omega log omega square, that will also not come from this G photon. Is that right?
Means the self-energy kind of diagrams?
Yeah, the self-energy kind of diagrams, yes.
Yeah, I expect at least the leading non-analytic structure, which is say in loop order omega to the power n minus 1 log omega to the power n. So this would not be affected. As far as I means in my some analysis I have seen that this would not be affected, but the lower order, say omega to the power n minus 1, there it could affect. But the leading non-analytic structure in omega going to 0 in n loop order will be this kind of analysis, omega to the power n minus 1 log omega to the power n, and so that this would not be affected by the self-energy. Okay. So then if you sum over these two kinds of diagrams with the G photon and restrict your loop momentum region in this thing, and you sum over all the contribution, and after some research, you can find that you can write down the full expressions and divide by this I lambda factor, whatever you have, you can find what will be the, how the subleading soft factor will look like. And surprisingly, you will find that one can write it down in this simple form. Some K electromagnetic factor, whatever we have done, whatever we have extracted using the K photon, the exponential edges, but now this will be regularized in the loop momentum integration. So what you will find is that this can be written. So what is this regularized clause? It's the same expression whatever I have written for the K electromagnetic regulated, but K electromagnetic piece, if you exponentializes, but now not loop momentum going to 0, but it is restricted to runs from omega to some finite energy particles momentum. This is the regulated, means that the loop integration is regulated in this region. Epsilon, and then, and if you approximate in this loop momentum integration region, that will become A dot small l minus, I think, plus I epsilon, and PB dot small l minus I epsilon. Okay, this is what it is. So finally, you see that basically you are left, if you can evaluate this integral, then you will get what will be the logarithmic soft factor is. So basically now our goal will be to evaluate this integral. I will not evaluate it, but I will tell where the poles of these integrals are, and then what would be the result. If you
so Biswajit, at
yes.
what order the integration range 0 to omega, at what order in omega will that contribute?
No, the integration is from omega to some PA. Mu.
Yeah, that contributes to log omega, that I agree.
Right.
But you also, I mean, when you do the integration, you do the full integration from 0 to infinity, I suppose. So from 0 to omega,
it will, from 0 to omega, the structure will be like so this we have computed directly, and just I am relating this factor, as you can think of as a differential operator operating on K electromagnetic. But if you evaluate this, if you evaluate these two diagrams in all loop momenta, and if you try to analyze that when the loop momentum is much smaller than omega, you will see that this goes like d4l upon l cube. So that can, in that region, it does not contribute to log omega, and it is not also IR divergent.
I see. So it probably gives some constant kind of thing.
Yeah. It will give some omega to the power 0 piece. It will correct. Because the upper limit will be omega, so it will give some omega to the power 0 piece corrections. And
so when you say that, when you say that it contributes to omega to the power 0, that means previous subleading soft factor that we earlier had.
Yeah, that would get corrected. Yes, sure. That would get corrected. And also, like, we have approximated in this integration regions and thrown many of the terms. So if you keep all these terms, those will also have omega to the power 0 corrections. So we are throwing all these omega to the power 0 corrections, and it is very hard to find out what will be the omega to the power 0 corrections taking care of all these terms. So yeah, if I have copied something, let's see. Okay, so basically that means you have to do a integration where you have three kind of poles. So one is photon propagator pole, and the other two are basically finite energy particles propagator pole. And if you do this integration, first you have to do the L0. For L there is a L0 integration, and then you have to integrate about the 3 L momenta. So for L0 integration, you can use contour prescription to do that because there are many poles. And let us see what are the positions of these poles. So let's consider for a moment that both A and B are incoming. And for incoming, we know we are considering the momentums are always positive, all the components, right? For outgoing, it will have a negative sign. So for incoming, all are positive. And if you see for if A and B both are incoming, the pole structures are from the photon propagator, the pole is so this is complex L0 plane. Okay. And minus I epsilon. So you see that if both A and B are incoming, then you, to evaluate this integration, you can obviously here close the contour in the upper half plane or the lower half plane both, but you have to take care of the contributions of the two poles, right? And what you will see is that if one of them is, so suppose A is incoming and B is outgoing, then what you will see is that this has a structure, the photon have the poles here, but now the finite energy particles have propagators have poles in the same site. So there you can deform the contour in the say lower half plane, and only you have to pick up the contribution from the photon propagator pole if one is incoming and one is outgoing. So what it is telling is that, what I will show next is that if both are incoming and both are outgoing, there are two kind of contributions. One is coming from the finite, suppose you close the contour here. So one will come from the poles of the finite energy particles, one will come from the poles of the photon propagator. And what I will show is that the contributions coming from the finite energy particles exactly reproduces our classical logarithmic soft factor, which we have shown earlier. But there is extra contributions which coming from the propagator pole of the photon, that is new, and this is completely due to the due to the quantumness of the H matrix analysis. Basically, what happens is I will explain how to get the classical thing. And the other thing is that what happens is that when A and B, one is incoming and one is outgoing, only you will get contributions from the photon propagator, and that is only the quantum piece. There is no classical piece, and you can assume that that is also what we explain is that long range force for outgoing particle will feel long range force only due to the outgoing particle, not from the incoming particle. So classically you should not expect this kind of contribution, and this also emerges from the pole structure of this integral. So let me maybe write down the from different region how the, if you evaluate the integration, what you will get. So from the pole of the finite energy particles, this only contributes if both the particles are incoming or outgoing. Yes. So I think I have a I by 2 p dot pb. So let me multiply. Okay. Electromagnetic, let me call prime, or maybe I should call classical. I will explain how this will give the classical contribution that will have a structure like I by 2 times UA QB, whatever you have, and then you already have the sum over a comma b, a not equal to b, also a pa dot pb factor from the numerator, and then with this what you will get is basically 1 upon 4 pi log of omega inverse square root over of pa dot pb whole square minus a square pb square times delta of eta a eta b is 1, which is telling us that in the sum you have to only take care of if both the particles are incoming or both the particles are outgoing, then only eta a eta b equal to 1 will be satisfied. And if you substitute this thing in the expression here, you will get the you will evaluate and you can show that the classical soft factor whatever we predicted, you will get the same soft factor from these expressions. But there is some extra contributions which we just explained, which comes from the pole of the propagator, role of the photon propagator. And these extra contributions, if you compute, so let me call it quantum, which has a PV factor, and then this turns out to be the contributions, and you have to substitute there in the like the differential operator S1 operating on this thing to find out the logarithmic extra logarithmic terms. And like you can see, this is the factor which was not present in the classical analysis. And if you take the classical limit, say like the energy of the gravitational radiation is small, in a sense impact parameter, large impact parameter limit, or you take one of the charged object to be very very large charge and the other is a test charge which is a very small charge, and in that limit if you try to also analyze, so you will find that this extra piece which is coming from the poles of the photon propagator, which we are calling the quantum piece, that is suppressed relative to the classical piece whatever we have. So but beyond that we don't have a better understanding of this quantum piece, because but you see that both are coming from the same loop integration region, same expression, so it is not suppressed by H cross. So we are not sure that whether even this is quantum or not, but in the classical limit some of this factor is suppressed. So we may expect that maybe this is a back reaction term, because you know when the energy transfer is very small, then the energy loss of the particles is small. So probably then this kind of terms will be suppressed. So we describe this thing as kind of a back reaction effect. But I think still we don't have a proper understanding of what this quantum factor tells us. So is there any comment or question?
Yeah, so when you say they are suppressed in the large impact parameter, what is the scale by which they are suppressed? Can you...
Okay, so if you like to take the impact parameter to be b, so at least I have checked numerically in mathematical, like say if the leading soft factor is supposed b to the power 0, say independent of b, for example, means you can factor out say whatever the 1 by b factor is there, then compare both the term, like up to suppose 1 over b square or b cube term, it vanishes. Means I don't know whether it vanishes to all order because we have not able to show, but it is suppressed like 1 over b square, all these powers turns out to be vanishes. Maybe it will affect in much higher order.
Okay.
Yeah. So let me then explain just so two observations what we observe here, and then I will mention the extra subtleties in the gravitational case and what the analysis would be there. So one thing is that you see is that if you naively assume that the tree level, suppose you naively assumed that the tree level soft factor is correct, even for the IR divergent S matrix. This is assumption. This is observation 1. Corrective in full IR divergent S matrix. Gamma n comma 0 and gamma n comma 1. And you naively assume that, okay, I will expect for the full IR divergent S matrix, I will have this S0 factor, and the tree level S1 factor, I am calling this S at 0, which is a differential operator, contains a orbital angular momenta, which is a PMU del del PNU minus PNU del del PMU kind of term. And then suppose it operates on the gamma n comma 0. Now what we have seen that after this KJ decomposition, we can able to write this thing as gamma n comma 1 times k, like, okay, so all loop order I can write as e to the power k electromagnetic times gamma n comma 1 with g photon, and this I can write e to the power k electromagnetic times gamma n comma 0 with g photon. And since now the tree level subleading soft factor is a differential operator, so when you commute this exponential through this factor, it will pick up a factor like S at 0 operating on the k electromagnetic. But this k electromagnetic is like the whole k electromagnetic. Now you prescribe an ad hoc rule that I will evaluate this k electromagnetic not for all loop momenta, but say in the regulated region, which I explained is the loop momentum greater than omega. Then also you get, without any like computations of this like G diagrams with the G photon, you can get still the full logarithmic soft factor. But this is just an ad hoc rule which I explained, but this is somehow telling us that, like, though we have derived, since this exponential to the power k electromagnetic is exponentiated from both n and n plus amplitude, and by assuming tree level soft factor operating on this thing naively is true. But since this k electromagnetic soft factor, though it is exponentiated for summing over all loop, but it is determined in terms of one loop only. So though we have done the analysis only at one loop order, but still our result is in a sense one loop exact. Okay. And obviously there are some other reasons, because if you dimensionally count also, it turns out that only one loop contributes to one log omega term, which I am not telling here. Okay, the other observations which I want to make is that if you replace the Feynman propagator in the analysis for the photon just by the retarded propagator, vector square, which is what we defined as the retarded propagator for the photon in the classical analysis in the momentum space, then you will see that only you will get the classical log omega piece, not the quantum piece. So this is somehow suggesting that what you do is that if you replace the from the quantum amplitude, if you replace the Feynman propagator by retarded propagator, there is a chance to get only the classical contributions, even if you try to do in higher loop analysis. So this is also giving a like prescription how to derive, how to get the classical analysis from a quantum thing. And I think if you remember this Barnett all their analysis, what they will do is basically they will do the similar thing. They will always evaluate, consider this photon propagator to be kind of a on-cell propagator, putting this propagator to be delta L square, and evaluate this thing to extract the classical result. This is in same analogous sense. Is there any question up to this point? Okay. If not, then let me proceed. So now I'll explain like all these things are good for QED, and obviously KG decomposition was already available earlier, so we don't have to struggle too much to derive all these things. But what happens for gravity? Like if we run the same arguments, can we do KG decomposition? Whether all this exponentializes thing happens very nicely, and is there any extra kind of subtlety which we have to handle? So what happens is that, yes, one can do KG decomposition using the same principles for deriving KG decomposition, which I explained for the QED case. but now it is very complicated, so I'll not write the expression for k mu nu and g mu nu, but in the note it is written. So here you can also, if you have a graviton propagator, momentum L, which you know in here also, if you use the Feynman gauge condition with the, that it will take structure like mu rho nu sigma plus eta mu sigma, sorry, mu rho minus eta mu nu eta rho sigma, and you can again break it similarly epsilon sigma plus some g for graviton propagator or sigma, and you can do the analysis. But here, this like the exponentiation for the endpoint amplitude, though it happens, but the n plus 1 point amplitude, the exponentiation is not clear to us. Means even we have not checked that n plus 1 point amplitude with our KG decomposition, it works or not. And the problem for this is what I'll show here. Like, so with this KG decomposition, if you attach the K graviton, say here, it will work like the photon similarly, that you will be able to write down in the similar breaking procedure. But if there is some external graviton is there, the nice way what we have shown for the photon case here, while we are showing that whether this similar kind of decomposition happens if in presence of external photon, for that we need to show that these three diagrams vanishes, and this was crucial, how like all the K photons are only attached to extreme right and extreme left, and that will help us to exponentiate for both n and n plus 1, but that does not happen for the graviton. And what happens is that now if you try to, now the analog of this thing is that these three things is not equal to 0. It contains some non-factorized term, but good that this non-factorized term is not IR divergent, but it can contain some log omega correction in the integration region what we will take. Like if you have a diagram, even with the K photon, you cannot exponentiate fully due to this some non-factorized contribution, but the whatever exponentiates that contains the full IR divergent piece, but some non-exponentiated part could be present that is not IR divergent but IR finite, but that can contribute to log omega, and that is separate some contributions which we have to analyze. So you have to compute all the diagrams with the G gravitons. With this extra non-factorite term with the K graviton, you have to also take care of. This is one of the subtlety happens in case of graviton. The another subtlety is that we have make this KG decomposition when the graviton is K graviton is connected to the scalar line, but there could be diagram in n gamma, there could be diagram in gamma n comma 1 where there could be 3 graviton vertex. So these diagrams, or maybe this kind of diagrams, and there the KG decomposition has not been done, and it is also not needed. But because but what happens is that this kind of diagram contain extra divergent piece, which is not present in gamma n comma 0. So this part we have to analyze using some IR cutoff. Say for energy, this is R inverse, which is the detector resolution. Okay, but this also contributes to log omega, but with this also it has some higher divergence which is not present in gamma n comma 0. So this is extra thing what we have to do. So these are the two extra subtleties we have to take care of. And then finally, it turns out that here also with the kind of diagram, whatever is there for the photon case, with this is the G graviton. This is also G graviton, and if it is connected, if the external photon is connected right to the loop, that vanishes in the same logic from the construction. But now you have to compute these diagrams with the 3 graviton vertex. And if you sum over basically this kind of diagrams and approximate the integration region in the integration region when the loop momentum is greater than omega, you will see that some of these contributions also contributes to logarithmically divergent factor, and logarithmically divergent factor with the lower limit of the integration is omega. So this also can contribute to log omega. But with this, what we have explained is that there is some another higher divergent contribution extra from this kind of diagrams is there, that also you have to analyze, and that comes from when the loop momentum region is much less than omega, and from R inverse, which is the IR cutoff what we have done, and that basically precisely gives contributions to the phase factor which we have described in the classical analysis with its corresponding quantum part coming from the graviton propagator's poles with its quantum counterpart. Okay, and then if you sum over all these diagrams and try to analyze, what you will get is basically the subleading soft graviton factor turns out to be, in a sense, the tree level differential operator for the subleading soft factor operating on mu operating on this some gravitational K part, which is also a classical part, and you have to evaluate also a quantum part. Sorry, GR quantum piece coming from the poles of the graviton propagator, and then you operate this thing. But with this, from the earlier side which you explained, when the loop momentum is smaller than omega, you have to also analyze this integration, and that also gives another log omega contribution with also a below limit log R. So that basically gives you I upon 4 pi log of omega times this whatever we have for the classical phase factor Pb dot k times S0 mu upon Pa dot k, but with this it's quantum counterpart, which I'm not writing. Okay, so this is what you will get the full subleading soft graviton factor, classical plus quantum. So is there any question? Because I think I go a little fast.
Yes, regarding this KG decomposition for gravity, so you're basically doing the KG decomposition in the same spirit as you did for photon, right?
Right.
And then you see that you still have some extra contributions left coming from the G graviton.
Yeah, the extra G gravity. Yeah, this is there because this KG decomposition is done only for the scalar lines when the graviton is attached to a scalar lines. Right. And these kind of diagrams are intrinsic only in gamma n comma 1, but not in gamma n0. So this, if this is divergent, it don't cancels between those two things. That's why we don't need to also KG decompose the when the graviton is connected to a graviton line.
I see.
Because you know it will not cancel anyway, so we just kept as it is.
I mean, can this be an artifact of the way you are doing this KG decomposition? Meaning, do you expect there may be some other alternative way of doing this decomposition such that you can collect all the terms from one of the, let's say the K graviton in that case, and just as you did for photon, like the G photon, those do not contribute to any IR divergence part.
Yeah, means one can break it down, then from the K part one can do, but still then doing this, you will so see that in gamma n comma 1, there is some e to the power k gr whatever you have, but with that you have some extra k tilde gr, which comes from 3 graviton, 4 graviton or kind of vertex. It is possible, but we have not done this.
I see. Okay.
So it is possible to do, because I think this is the artifact of the gauge invariance, like because you know this metric related to the energy momentum tensor, this is a gravitational, like the covariant, like the gravitational energy momentum tensor is basically covariantly conserved. And for the gauge invariance, you need to include the gravitational energy momentum tensor, and this is, you can think of the quadratic part of the gravitational energy momentum tensor coupled to external graviton. So that's why this effect is there, which I will explain maybe in the next lecture.
I mean, does that mean that even if you do an alternative kind of decomposition, then also this this problem will be there, because as you mentioned that gravitational
so this is not a problem, means this is just we have to do a little hard calculations and we have to analyze little more diagrams, but this is intrinsic, like you cannot remove this thing by doing some another way.
Because you correct me if I'm wrong, I was thinking of this KG decomposition as you have a function and you are basically segregating the function into the singular part and the regular part.
Right.
And it worked well for photon, because you can collect all the IR divergence piece from one contribution, meaning from the K photon. But in the case of graviton, as you see that like this decomposition, you still have some contribution left from the other piece.
Right.
Okay, but that cannot be easily removed.
Yeah, that's means that has a physical interpretation, and it's like it's not removable also. Means if you cook up some other thing, you can make that from the IR divergent piece from this kind of diagrams also, you can picked up separately, but it will not be cancelled from both sides. So it is intrinsic there. You have to analyze this thing. And you see that basically precisely give the phase factor, whatever from the classical analysis we have seen the backscattering effect of the, if some graviton is gravitational wave is moving in a curved background, and its quantum counterpart also. So maybe like the quantum analysis, the quantum result we have explained in such a way that what happens is that due to the classical piece is what it is telling, that due to the asymptotic trajectory are not straight line, they are moving, they are accelerating due to long range force, so they are emitting radiation. Now what happens is that due to this radiation energy loss, the trajectory will also get corrected, and that back direction effect is taken care of by this quantum piece. And this is how we interpreted it, because of the fact that when the gravitational energy loss is small, say large impact parameter or probe scatter limit, this quantum term is suppressed. That is why we have given interpretations like that. But probably like one can have some independent understanding of this quantum piece from some analysis, which we don't have yet. Yeah, is there? So I will not proceed today more. So if only if there are any questions, so I can ask, or I will finish here. So please ask question if you have not understood anything in the last 2-3 minutes.
So Biswajit has actually finished 2 minutes earlier than his scheduled time. So first, let us all thank him for this nice lecture. Since we have time, please ask questions.
Okay, so can I ask some general questions?
Yeah, sure.
So you talked about this classical limit by taking the poles from the retarded propagators, basically replacing the Feynman propagators by retarded propagators, and you get the classical soft theorem.
Right.
And then there is a some other formalisms like developed by Koswar et al., which
Right.
Atira Manu have worked on that.
Mhm.
So, are they equivalent to each other? Meaning, is there any way to see relations between these two formalisms?
Yeah, I feel that they put these things to be on sale, right? The proton propagators they put probably on sale before even doing the loop integrations. And you see that means basically in place of 1 by L square plus I epsilon, they're putting some I pi delta L square kind of factor, if I correctly remember. And I think means then basically like, yeah, somehow I don't know. Okay, maybe Manu can say, means I'm not that much familiar of this Kosar formalism.
Atira Manu, if you want to comment.
Atira, do you want to take this?
Yeah, so basically, yeah, as you were saying, so instead of the matter propagator, we have the exponential delta function.
Mm-hmm.
So
Right.
then the residue actually cancels. I mean, it's zero in the quantum propagator.
So there is a consistent way of setting the Feynman propagator to retarded propagator.
No, it is actually Feynman propagator, but
okay.
the contribution from the Feynman propagator, that is zero.
I see. Okay.
So the poles from the photon propagator, you will always have zero, and we have to only pick up the poles of the finite energy particles. Okay.
Yeah.
So that is already inside the construction of Kosar.
It's simply, I mean, that is how he has formulated the full analysis.
Just a little side comment. So the cancellation actually comes from the on-shell conditions of the particles. So,
okay.
I mean, there is a phase space integral which goes like d4L by 2 pi to the power 4, 1 by L square, which is the Feynman propagator, times delta of P1 dot L, delta P2 dot L.
Okay.
Mm-hmm.
So because of the delta functions, those come from the on-shell conditions of the particle, and because of the fact that you have a delta P1 dot L and delta P2 dot L, the Feynman propagator, which is like the L0 equal to 0, L0 equal to mod L, that contribution cancels, like Adira said.
Okay. Means you are telling that they are in the phase space integration, you have delta function of the finite energy particles, and first you have to evaluate using this delta function the L0 integration, and if you do that thing, then you can see that the 1 over L square there is no pole left out.
Yes, exactly.
Yes.
So this on-shell condition, are you putting it by hand or like where does it come from? I'm a bit confused.
Adira, you want to?
Not putting my hand.
Okay.
No, actually it comes from the way they defined the classical observables. So it actually comes from so the classical observable expectation value is defined as like you take an in state, you operate it with the S matrix, and I think in one of those slides where Biswajit had written expectation value of a bra P1 P2 S
in the coherent state.
But just not the coherent state, with the coherent state being replaced with the S matrix.
Okay.
So now when you insert complete set of states, you will see so those complete set of states are on-shell condition, on-shell states basically.
Okay.
So that's where the on-shell conditions actually come from. So it is actually inbuilt into the formalism basically.
Okay. Yeah, maybe you people can give a talk on this, then we can understand better.
Also, I guess in the Hamilton school, Kossover is speaking, right?
Yeah.
Maybe Subramanya, you can stop the recording now.
Yeah, let's ask people if there are any further questions. People can go ahead and ask. Otherwise, we will pause the recording and people can ask questions more informally.
Biswajit, just one point. So regarding the gamma n gamma 1g,
right?
So in the paper, so there were two contributions. There were two integrals, if I remember correctly, I1 and I2, and when you add them up, then that integral in the regulated region can be written as S1 hat.
Right.
So like you said, so when in the 0 to omega region, k greater than no, sorry, k greater than L. So
Right.
that is a IR finite quantity. Like
Yeah,
you said,
this
D for L
goes
by
like
Q.
D for L by L cube, right?
Yeah, but looking at the expression, it also looks like it has a 1 by omega piece.
No, I think it don't have
Maybe
like maybe in the lecture note also I have copied from paper, and I think you can see that there.
Okay, I'll check
Yeah.
it once. Yeah.
Yeah.
Okay, I'll get back to you.
So sorry. So yeah, you are right. So this is a 1 over omega piece, and then it is loop momentum is going like d cube L over L d4 L over L cube. So that will give 1 omega,
Right.
and this omega cancels and give you a order omega contribution.
Right. That makes
And
sense.
which is log omega is leading than the order omega.
Right.
Yes,
You're
yes,
right.
You are right. Yeah, I just forgot.
Right.
Right.
Okay, then let me go ahead and pause the video. Then people can continue the discussion more informally. Okay, so welcome back to the post-lunch session. We will continue with the last lecture on supergravity by Subbu. Over to you, Subbu.
Okay. Yeah. So I'll start with a recap of what we were doing. Okay. So there are some things to clarify before the recap, which are like some things which were not directly related to the lectures as such. Like someone asked when I was doing the recap last time about this representations in higher dimensions, what would happen? Okay, when I still don't know the answer, but I had said the 0 sigma mu sigma bar mu 0, this Weyl representation exists in every even dimension, which is true. But both Neetu and I got the dimensions wrong. Okay, so basically we counted the number of dimensions of the complete Clifford algebra, okay, which told us like what should be the dimension of gamma matrices, like what dimension complex matrices does the complete Clifford algebra span. Okay, and it was 4 cross 4 in 4 dimensions. Okay, but in 2n dimensions, it is 2 to the power n cross 2 to the power n. Okay, and this block is half of that. Okay, so 2 to the power n minus 1 component Weyl spin. Okay. So there will definitely be a chiral sector and an anti-chiral sector. Okay, but I don't know more details about the representation theory after that. Okay, so that is one thing. And another thing is that okay, so last time, so let me begin the recap and say the other things along the way. So last time we considered this gauging the superconformal algebra, okay, where for each of the generators, PA, MAP, D, KA, lambda ij, T, I guess, or lambda T, I don't remember, QI, SI. For each of these, we associated each generator with a gauge field. Okay. V mu ij, A mu, psi mu I, phi mu. Okay. And just like the earlier case, okay, where we had the gauge theory of the conformal algebra, and we needed to delete translations so that we have a nice definition of covariant derivative, okay, for the matter fields. And also that also because we want to have this theory realized on space time, okay, so we replaced it by covariant general coordinate transformation. So here also we will replace delta P by delta CGC. Okay, and when you do that, okay, if you just like before, let's say if you demand these to be equal on E mu A, so that you can say E mu A is the generator of covariant general coordinate transformation, then you will get Rp mu nu A is 0. But by supersymmetry, okay, so see, would also give us gamma mu RQ mu nu I is 0 and RM mu rho, sorry, RM mu rho nu rho is 0. Okay, where I have taken trace over the rho index. Okay, it will soon appear, I guess. Okay, so these conditions, they form a multiplet under SUSY. Okay, so the another change that was there from the conformal algebra was that QQ closest to P, right? So here, if you demand QQ closest to CGCT, then also you can derive these constraints. Okay, which is very neat. Okay, and after you impose these constraints, you have the independent fields as E mu A, B mu, V mu ij, and A mu, and psi mu I. Okay, omega mu AB is made dependent by RP constraint. F mu A is made dependent by RM constraint, and phi mu I is made dependent by RQ constraint. Okay, once you solve these constraints, you will get the expressions for these independent fields in terms of independent fields. Is that clear so far? Okay. So next, so there was a concept I introduced, but I was a bit hurrying. Okay, so the terminologies may have got mixed up. Okay, so there is a notion. So when we do gauge theory, okay, then we realize the algebra on fields, okay, by two methods. Okay, this is some general field phi. Okay. Then the whatever is the symmetry algebra acting on this field, okay, it will be realized using this as well. Okay, sorry. Delta epsilon 3 phi, where epsilon 3a is FBCA, epsilon 1b, epsilon 2c. Okay, this some people define it as epsilon 2b, epsilon 1c. Okay, it's a convention. So we also have TA, TB is equal to FBCA. Okay, some people define it with an I and so on. So I'm not paying too much attention to these conventions. Okay, we all know how to do it. So in gauge theory, right, like for example, non-abelian gauge theory that we do in our quantum field theory courses, okay, both of these are true. Okay, so abstract generators, of course, from group theory, they satisfy this algebra. Okay, and if you take the transformations on fields, okay, they also realize this algebra. This is what we mean by saying field will form a representation of the algebra. Okay, so this is also true, but we can have two concepts. Okay, one is known as the soft algebra and other is called as the zilch symmetry. They're both related to the fact that we can take this as the fundamental definition to generalize to more general gauge theories. Okay, in particular gauge theories including which include space-time generators, for example. Okay, so if you take this one, okay, then because the fields are already involved, okay, the right hand side can have many more features. Okay. In the case of the soft algebra, we will have field dependent structure constants. On the right hand side of the algebra. Okay. Or okay. I mean, actually, there are many ways to say this. So let's say field dependent transformation, gauge transformations on the RHS. Okay. And the next one is zilch symmetry. Okay, there could also be equation of motion on the RHS. Okay, or terms proportional to equation of motion. Okay, so this happens for the case of on-shell supersymmetry. But this does not, of course, give any new symmetries in the theory, because the Noether charge will just go to 0 on solutions of equations of motion. Okay, and also you can show that with given any theory with more than one field, okay, you can always define a Zilch symmetry. Okay, the proof is there in Friedman and Van Proen, for example. Okay, so this happens for the case of on-shell superstructure. Now, when we take this kind of a generalization, okay, there are two things that we had earlier demanded from covariant derivative. Okay, so here I had slipped and I had miswritten something. Okay. So the two demands are, one is that it should not contain, it doesn't contain derivatives of, I said gauge fields, which was wrong. I meant derivatives of gauge transformation parameter, okay, which is the whole point of introducing covariant derivatives. Okay. So that is one demand. Okay. Now, I guess we all understand this. And the second one is that it forms a representation of the algebra, okay, with these structure constants, right? So when you say algebra on fields, you mean this, that epsilon 3a is indeed given by FBC A epsilon 1b epsilon 2c, which is the same FBCA as this algebra, okay, this abstract algebra, okay. So whenever this happens, right, suppose there is some algebra which has some structure constants, and it is realized on fields with the same structure constants plus some field dependent gauge transformation terms, you call them by the same name, okay. You call, if this is superconformal algebra, this also you call a superconformal algebra, okay. Yeah, so are there any questions about this? Okay, so okay, let me just say that these notions are equivalent for usual gauge theories where we have the hard algebra, okay. Whereas if we have this, when we have this general notion, okay, then only if the algebra closes off shell, okay, we have these two are equivalent, okay. Equivalent if off shell SUSY is there, okay, or the algebra closes off shell. Okay. Are there any questions? Okay. So because we need off-shell closure of the algebra so that we can have this equivalence and we can use the covariant derivative, okay, which forms a representation of the gauge group so that things are simpler to manipulate. And also, if we have off-shell representation of SUSY, we can construct general actions, okay. So therefore, we need off-shell completion. So we introduce auxiliary fields, and for n is equal to 2 conformal supergravity, okay, we have for n is equal to 2 conformal supergravity, we have TAB, which is an antisymmetric tensor, so it has 6 components, and D, which is a real scalar, so 1 component, so 7, and chi, which is doublet of Majorana fermion, so 8 fermionic components. So if we add 7 bosonic and 8 fermionic components, okay, to the already independent components we had, okay, and subtract the number of gauge transformation parameters, we get 24 plus 24 standard Weyl multiplier. Okay. As I told yesterday, there is a different version which has the same feature, that it contains all the gauge fields of the superconformal algebra, but different auxiliary fields. Okay. So which is called as the Dilleton Weyl multiplier. In particular, it does not have these auxiliary fields, which will become relevant today later. Okay. So then we studied what are the matter okay. So another thing is, yesterday, I don't know if I confused people. When I went to current multiplet approach, I called energy momentum tensor as T mu nu, but that is not the same TAB. So today let me call the energy momentum tensor theta mu nu. So what happens is that you have this current multiplet. Okay, let's say for super Yang-Mills, it will have the energy momentum tensor coupling to graviton, and the supercurrent coupling to the gravity no gauge field. Okay, yesterday I might have written both IAP. Okay, and then you have the first order action. Okay, so what happens is that when you impose Soucy invariance of this action, you get transformation of these fields from these currents. Okay, so when we do that, conserved currents such as theta mu nu, j mu I, they lead to gauge fields such as graviton and gravity. Okay, but there are also non-conserved currents such as scalar field D, which sits in the current multiplet, so that current multiplet is closed under supersymmetry algebra. Okay, and that couples to a real scalar field D, okay, which should be the auxiliary field. Okay, so just by working out the n is equal to 2 super Yang-Mills current multiplet, we know what auxiliary fields to add to obtain the standard Weyl multiplet in conformal supergravity. Okay, is this clear? Okay. So then we went to the case for matter. Yeah.
This auxiliary field in standard Weyl multiplet. This TAB is this anti-self-dual anti-symmetric Lorentz tensor, right?
No, I mean there are two ways to
also,
look.
TAB, IJ.
Okay. I mean, so this is SU2, right? So if you have antisymmetric epsilon ij, you can just take it out. Okay. And then what happens is that you get T minus AB, T plus AB, and anti-self-dual and self-dual. If you add them, you get a real TAB. Okay. So you can either think in terms of a real TAB or a complex T minus AB. Okay. So if it is real TAB, it is, so the counting just changes because of that. In one case, it is 3 into 2. In another case, it is 6. Okay. But it's the same thing. Yeah. Okay. Yeah. So, okay. Are there any other questions? All right. So then we considered the case of matter multiplets. So we considered vector multiplet, which has these fields x, omega I, w mu, and yij. Okay, and this is an 8 plus 8 multiplet. And this x transforms under both dilatations and it transforms both under dilatations and U1R transformations. I think it has C is equal to -1 and W is equal to 1. Okay, but this you can check in some book. Okay. So later we will use it to gauge fix both U1R symmetry and dilatation symmetry, just like how I said yesterday. And this transforms under S supersymmetry, okay, to just the to x times. So del S omega I will be some proportionality constant times x times eta I. Okay. So this is used to gauge fix the S supersymmetry. Okay. So whenever there is a single, so when what one does is there is always a single vector multiplet compensator, and when you go from conformal supergravity to Poincare supergravity, okay, one fixes x is equal to x bar, which gauge fixes U1R symmetry. That is equal to 1, gauge fixes dilatations. Okay, and omega I is equal to 0, gauge fixes S supersymmetry. Okay. Now W mu is remaining. Okay, and this is the field that will give us graviphoton. Okay, when we go to Poincare supergravity. Okay, you might remember that when we considered the representation theory in n is equal to 2, there was a graviphoton. Okay, and this is that field. And when you have more than one vector multiplet, okay, the case I told you yesterday, this condition can also be used, but people use a condition which is more suitable, okay, with respect to the pre-potential, but that I won't discuss. Now notice that SU2R symmetry is not fixed. Okay. Just keep that in mind. But there are other multiplets. For example, there is the tensor multiplet, which has the tensor gauge field E mu nu, phi I, doublet of fermions, complex scalar G, and some Lij, okay, which is a just like this one. This is the pseudo real triplet. Okay, so where Lij complex conjugate is Lij, which is epsilon Ik, epsilon J, L, Lk. Okay, so there is also tensor multiplet, which is also an 8 plus 8 multiplet. So for vector multiplet, the way one constructed an action is by relating it to the chiral multiplet. Okay, and chiral multiplet is 16 plus 16 components, and one has the nice feature. One has the feature that the lowest component transforms in a chiral manner. Okay, I think it is epsilon bar I psi I by 2, and it is S invariant. Okay, and the highest component transforms to a total derivative in flat space. Okay, so here it transforms to some epsilon bar d slash of something. Okay, plus other term. Okay. Using this, one can write a density formula, which is given here. Okay, so here what happens is that, as you can see, this is the first term, right? So the second term comes because when you take this d, right, the derivative outside to make it the total derivative, in flat space, epsilon is like a global symmetry, so it did not depend on position, so you could take it outside. But here you will have a derivative of epsilon, which is d mu epsilon. Okay. So because of that, you need to add the gauge field. So replace this by psi mu and add another term, okay, which has psi mu, lambda, and epsilon, psi mu, lambda, and gamma, okay, which is this term. Okay, that cancels that part of the transformation. Okay, so it was total. So you could think of this term as total derivative minus d mu epsilon gamma lambda. Okay, but if you have another term which has psi, which transforms as d mu epsilon, then that gets cancelled. Okay, but then psi also transforms to t. Okay, there are some covariant terms. Okay, which is when we added auxiliary fields to the conformal supergravity. Okay, the transformation rule became a little bit complicated. Okay, therefore you will have to add more terms. Okay, so people went iteratively. Okay, seeing what are all the extra terms they get. Okay, and what they should add to cancel that term. Okay, so using this way, the full chiral density formula was constructed. Okay, and the interesting feature of this formula is that the multiplet which has this formula, okay, which is the chiral multiplet, it admits an embedding of other multiplets. Okay, we can write A is equal to x square, okay, and you take supersymmetric transformation of A, it goes to some psi, let us say. Okay, and you take supersymmetric transformation of x, it goes to some d slash omega or something. Now, what happens is in the next step, when you take the SUSY variation, psi and omega get related. Okay, and this psi indeed appears in the density formula at a later step. Okay, here, this is that psi. Okay, it is not the gravity, no, it does not have a space-time index. This is the gravity, no, this is the matter field psi. Okay, so that will have d omega of the vector multiplet. Okay, and once you substitute. Once you take the full SUSY variation and relate every component of the chiral multiplet to some combination of the vector multiplet, this full density formula will give you a kinetic action for the vector multiplet in supergravity. Okay? And you take that action, impose these gauge fixing conditions, right, which are given here. Okay. Then you get what a minimal supergravity action, except that this has SU2R symmetry because that we have not gauge fixed. Okay, and Poincare supergravity need not contain SU2R symmetry. And there is another problematic feature, okay, with this action. Okay, is this part clear so far? What was being done here in this slide? Okay. Yeah. So this is another problematic feature, which is that when one considers the action obtained this way, okay, the resulting action contains a linear term in D. Okay. This will impose some non-trivial conditions on fields because suppose you began with this action, okay, and said this is the Poincare supergravity action, okay, then the equation of motion for D, okay, because D is linear, it will impose a condition on other fields, okay, which cannot be satisfied, okay, due to whatever gauge conditions we have said so far. These conditions are not consistent. Okay, so there is this technical problem also. So the resolution is introduce a second compensator multiplet. Okay, and that for that there are three choices. Okay, one is called as the tensor multiplet, which I discussed earlier. Okay. Another is nonlinear multiplet, which I have not discussed here, okay, and but it is there in Mohab's lecture notes, which is a reference. Okay. And there is the hyper multiplet, okay, which is an on-shell supersymmetry multiplet. Okay. So tensor multiplet is off-shell, nonlinear multiplet is off-shell, but hyper multiplet is on-shell. Okay. But all these three are used to obtain Poincare supergravity theories. Okay, and all of these lead to minimal Poincare supergravity theories. Okay. So to construct the action for tensor multiplet, okay, a non-trivial procedure was used, okay, where one used this fact about dualization, okay, which we were discussing in Biswajit's lectures a little bit, okay, or on Slack, okay, to show that tensor multiplet has the appropriate degrees of freedom as a free scalar, which is the hyper multiplet, okay. So such an action was constructed by Bernard David and others, okay, in this paper called Improved Tensor Multiplet in N is equal to 2 Supergravity in 1983. Okay. So in the same paper, they listed all the minimal Poincare supergravity theory, okay, with these compensators. Okay. So when you introduce these compensator multiplets, okay, what happens is that, so for example, if you consider the tensor multiplet, then it has this field Lij. You can break SU2R symmetry to U1R, which is e to the power U delta Ij. Okay, and this so once you do this, and once you use the tensor multiplet action given by them, okay, what will happen is that you will get the Lagrangian, the D term in the Lagrangian will become 1 minus e to the power. Okay. Because in the tensor multiplet action, there was some Lij to the power minus 2 D term that was there, okay, in what they constructed. and already one had a term which was linear in D. Okay, so together they become something like this. Okay, and this will just fix the value of u. Okay, when you impose equations of motion. Okay, so and whatever was there with this B. Okay.
Subbu,
Huh.
can you explain this breaking of the R symmetry once again?
Okay. So, I mean, maybe I can do it in more detail, but based the later. But essentially, Lij transforms under SU2. Okay. But you can see, for example, here, if you take L12, it is e to the power u times 0. So you are setting L12 to 0. Okay. And if you take the U1 SU2 symmetry of L12, okay, this L12 is equal to 0 will break one of the generators of SU2. Okay. So similarly, if you analyze it carefully, two generators of SU2 are broken and only one U1 remains. Is that okay?
So these multiplets will be representations of that R symmetry group. Is that right? For example, if you take a tensor multiplet and the fields will be representations of that. When you are breaking that R symmetry, then how do you write the field contents then?
Oh, I mean, you could still write those indices, but they won't matter because once you go to Poincare supergravity, there is no R symmetry. So you can write them in any way. I mean, doesn't matter.
Okay. Thank you.
In the sense that they lose the meaning that they are indices of some symmetry. Okay. So more detailed analysis will be required, in fact, because even the gauge field is there, which is V mu ij of SU2 gauge field. Okay, that also goes to a non-trivial object when you go to Poincare supergravity. But I am avoiding all that. Okay, what the message I want to give people is that you have the 24 plus 24 standard Weyl multiplet. And you add 8 plus 8 vector multiplet. Okay, this is quite slow. And add 8 plus 8 tensor multiplet. Okay, or hyper or nonlinear. Okay, so you get a 40 plus 40 Poincare supergravity multiplet. Okay, but of course, if you use hyper multiplet, okay, the point, okay, not in the case of hyper multiplet, but if you use nonlinear and tensor, okay, that is 8 plus 8. Hyper multiplet is on shell and it is 4 plus 4. Okay, so if you use hyper multiplet, okay, you will get on shell SUSI, okay, on shell Poincare supergravity. Okay, so there are, but it doesn't matter. Like Poincare supergravity being on shell is okay. Okay, the important point for us is that conformal supergravity should be off shell so that we can construct general actions for these multiplets. Okay, so that we can construct general higher derivative invariants for Poincare supergravity. Once you construct Poincare supergravity, that can be on shell. Okay, so just like the chiral density formula giving action for one vector multiplet, chiral density formula also has actions for n vector multiplets by prepotential that I described last time. Using that, you get n vector multiplets coupled to Poincare supergravity. If you use n plus 1 vector multiplets, where 1 is a compensator, all the other n will remain as dynamical multiplets in Poincare supergravity. Okay, and so there are two things. One is n plus 1 vector multiplets in matter coupled supergravity, n+1 vector multiplets coupled to conformal subgraph. Okay, which will give you n vector multiplets coupled to Poincare supergravity. Okay, and some other and second compensator. Okay, that is also there. And the second thing is that there is also Weyl square action, okay, which is the pure conformal gravity action. For example, we considered the scalar field action, okay, when we considered the conformal gravity case without supersymmetry, but we could also consider the gravity action, which is the Weyl square action in conformal gravity. Okay. That also, once you set B mu is equal to 0, will give you Riemann square term, okay, in the Poincare gravity. Okay. So Weyl square action was also constructed. Okay, both these actions were constructed very long ago. Okay, and these gave rise to some. This gave rise to higher derivative action, Riemann square. Okay. And the first one gave rise to quadratic action. Okay. And recently in 2013 or 2014, Lodato, Butter, and Bernard David, they gave a new higher derivative action, okay, which gave Susi completion of Gauss-Bonnet term. And this was important to understand some features of black hole entropy computations, okay, because people did not have the Gauss-Bonnet term supersymmetric completion earlier, but Gauss-Bonnet term was still important in computing the higher derivative corrections to black hole entropy. Okay, so this work clarified some of the features. Okay, and this was done in 2013, I think. Okay. But I won't discuss this any further. And but all this happened in n is equal to 2 supergravity. So in n is equal to 4 conformal supergravity, the first action was known. It was constructed by Diru. Okay, I think in 1982 or something. Okay, gave n is equal to 4 n+1 vector multiplets coupled to Weyl multiplet, okay, which gave the quadratic action. And in 2017, okay, and or 16, I mean, they wrote many papers, or 19. Okay. So they wrote 3 papers. Okay, so basically Ciceri, Butter, David, and Sahoo for Bindusar Sahoo. Okay. So they gave n is equal to 4 Weyl square action. Okay. And this was harder to construct because of a technical reason. In n is equal to 4 supergravity, the Weyl multiplet contains some scalar field which has some spurious gauge symmetry. So the action was very hard to construct using the chiral density formula. Okay. So they constructed a new density formula in n is equal to 4 supergravity, which allowed them to write the Weyl square action. Okay. And they think that they have all the, that action is general enough to include all the higher derivative terms in n is equal to 4 supergravity. I mean, at 4th order in derivatives, okay, so curvature squared terms. So, so now in principle, I mean, one can start doing computations in n is equal to 4 supergravity for black hole entropy and compare it to string theory results, okay, because the string theory results were there for n is equal to 4, but then one did a truncation because people did not have n is equal to 2 invariant, 4 invariants available for them. So in the rest of the lectures, we will we will see what is the technique used to construct this density formula, okay, and we will apply it to obtain the chiral density formula, which we already saw. Are there any questions? So from now we will go out of supersymmetry and we will discuss something on more general lines. Okay. And we will come back to supersymmetry. This is called as gauge manifold approach. Okay. Where basically what you do is, suppose you have 4 bosonic dimensions. I mean, okay, 4 space-time dimensions. Okay, for now I think 4 is not required. Let's say D, because I'll take a 3D example soon. Let's take D space-time dimensions, and plus we have some gauge symmetry. Okay, what we do is we geometrize the gauge symmetry. Okay, geometrize the gauge symmetry. Okay, that is, you consider what is called as the super Weyl-Bein, which is EA and A alpha. Okay. So later it will in fact become super Weyl-Bein with Soucy directions, but right now it's a general term. Okay, this is the usual Weyl-Bein, which is EA is E mu A dx mu. Okay, and A alpha, okay, so is A alpha mu. I mean, if you want, you can write it as some other index. We are falling short of indices. Okay, this is the gauge index, okay, gauge group index. Oh, sorry, there is a delay. I mean, alpha is a gauge group index. Okay, so we generalize the space time. Okay, so we consider this manifold, okay, as a sub manifold, okay, in a larger manifold called M. Okay, manifold with both space time and gauge direction. Okay, so we are abusing the notation a little bit here, okay, because this would also have, like, A alpha would also have some legs along the gauge directions. Okay, the Weyl, it will also have A alpha, I don't know. Yeah, okay, I'll come to that later in the specific example. Okay, so basically we are generalizing the notion of the space time, okay, to also include gauge transformation. Okay. Are there any questions about this? Okay, so why is this useful, you might ask? Okay, this is useful because now gauge invariance can just be thought of as a subset of generalized diffeomorphisms, okay, in this larger space time. So we can define I as integral J on M, okay, which is a subset of M. Okay, this M is the 4 D space-time dimensional manifold. Okay. So
a quick question.
Yeah.
So in the previous slide,
yeah.
So along with the usual Weyl-Bein, you added this gauge field.
Yeah.
So is there, I mean, is this completely universal in the sense I can add anything, or are there some conditions that they should satisfy? Like, for example, omega mu AB is also a gauge field.
Yeah.
So can I just also attach it along with this Weyl-Bein, for example? Is that?
No, I mean, it should be a symmetry which is like not, how do I say it? Yeah, I mean, firstly, we won't have any dependent symmetry, okay, which is like.
But that is fact that you get to know later, right? I mean.
That is a fact. I think you can. I mean, I don't know, like maybe you can also use omega mu AB, okay, but okay.
So
But what I know is that, for example, in supersymmetry, okay, you can geometrize Q supersymmetry, okay, but you can also geometrize S supersymmetry, okay.
Okay.
It just gets a bit confusing, but that can also be done. But they both give the same answer. Okay, so this much I know, but from the perspective of the manifold, I have not seen like beyond the Weyl being added. In the sense that I don't know, like there is this prescription called as rheonomy. There is this principle that people call rheonomy, okay, which says that only the Weyl, okay, the gauge fields A mu, okay, and the, let's say like supersymmetry gauge field psi mu, okay, that should appear in the Lagrangian explicitly, which is what will happen, okay. And I think that is because these are somehow the physical degrees of freedom. But I don't understand this principle like further. Like, but in conformal supergravity, I know that you can geometrize both Q and S, or you can geometrize only Q, and the results are the same.
I see. Okay. So you call this rheonomy?
Rheonomy, yeah.
Okay.
Yeah.
Okay, I'll take it out.
Okay, yeah. Okay. So all these techniques are basically based on this. This principle generalized to SUSY is called as ectoplasm principle, okay, which was introduced by Jim Gates, and that is related to this rheonomy principle. Yeah, we will see an explicit example, and maybe some of these things will become clear. Okay. So now this J is a D form, okay, on the space-time manifold, right? But as in it's a D form on the larger manifold, okay, being integrated over, being restricted to this manifold. Okay, that is important to remember. D form in curly M. Okay, so you're basically taking, so this M is has dimensions greater than D. And you are taking a D form in that, and you are integrating over the subspace. That gives you the action, okay? Because ultimately action is an integral only on the space-time manifold, okay? I guess that is clear. So now the Lie derivative, okay, on J, I don't know like how many people know this here, but Lie derivative can be written in terms of what is called as interior derivative, okay, and this is the exterior derivative. So exterior derivative, what it does is that if you have like a P form, it will take you to a P+1 form. Interior derivative will take a P form and will give it to P-1 form. Okay, basically it will contract a vector xi mu with the P form to give the P-1 form. Okay, that is all an interior derivative is, up to some normalization. So you can just work out with the definition of Lie derivative on any field that it is equal to this combination. Okay. Is that okay? Are there any questions about this?
Sorry,
yeah,
maybe a trivial question.
Sure.
But is the structure of curly M cross something?
Sorry?
At least look the structure of the gauge manifold.
Yeah.
Is it locally M cross, where M is the space-time manifold? M cross something.
Oh, I think it's this fiber bundle structure, right? These gauge fields, I think are fibered over the manifold, but I don't know. I mean, I haven't studied the structure in rigorous detail, like how to describe it mathematically.
Just a comment on that. At a given point, a fiber is just M cross whatever the gauge manifold is.
I see. Okay. Yeah. Right. Yeah. Okay. Yeah.
Yeah, but sorry. So my question is that any D form in this curly M,
Yeah, yeah,
will they be equivalent? The indices can run over all the, all the
yeah,
space-time
yeah,
indices and the gauge
yeah, yeah,
indices, right?
yeah, yeah, yeah. They can.
So, then they'll all be equivalent.
They will all be.
Equivalent. For instance, what I'm saying is that this J,
Yeah,
uh, it's a D form in this curly M, right?
yeah, but for
But
I, yeah, but the I integration is over the usual M. So what we can do is like that. I will give the example of Chern-Simons non-abelian Chern-Simons gauge theory in 3 dimensions. Okay, so there some of these things will become clear when I show that that is gauge invariant. Is that okay?
yeah, sure.
Okay. Yeah. So now the point is that delta I, therefore, okay, under this generalized diffeomorphism, okay, is given as d ij, okay, plus ij dj. Okay. But then notice that this is a boundary term, right? So if you have suitable boundary conditions, okay, or if you have no boundary, okay, this term goes to 0. Okay. Therefore, the second term must go to 0. So if we have dj is equal to 0, that implies delta I is equal to 0. Okay. So in this generalized structure, okay, if this J is a closed 4 form in curly M, okay, then delta I is equal to 0. Okay, so we get a generalized diffeomorphism invariant action, and gauge invariance is a subset of that. Is that clear? So we will do this now for non-abelian Chern-Simons gauge theory in 3 dimensions, and then go to supergravity.
For delta I.
Hi Ashwin, we couldn't hear you. Can you just ask your question again?
Oh,
Hello.
Hello. Yeah.
Can you hear me?
Yeah.
In the previous slide, what kind of delta you took?
Oh, delta is delta xi. Okay, it's the when you take. So I just did a Lie derivative on J, okay, and that is this delta I. So in usual GR it would be diffeomorphism. Here it is generalized diffeomorphisms, which also involves gauge transformations.
Subbu, I'm confused about that statement actually. So
yeah,
if I think of this diffeomorphism as a combination of both space-time diffeomorphism and a gauge transformation.
Yeah.
Then shouldn't it like so? Okay, so capital D and so the exterior derivative is it on small m or capital or curly m?
Curly m.
So the exterior derivative is on curly m.
Yeah.
So then why is Stokes theorem valid in the integral over space-time M?
Why is
like if the exterior derivative is on full curly M, Stokes theorem should be the boundary of.
Okay. Okay, maybe we can discuss with in Chern-Simons gauge theory. I think what happens is that even though it is on curly M, for the integral it is evaluated at M and then integrated over, I think. So maybe we can do it for like Chern-Simons theory and it might become clear. Is that okay?
Okay, fine. Yeah.
Okay. Yeah. Okay. Yeah. So now what we need to do is consider a gauge field in 3D. It transforms like this. Okay. Okay, so this is the gauge transformation. Okay, and we will propose a J okay, where all we have wedge products. Okay, so we need to show that this is gauge invariant. Okay, so we have defined a larger manifold. Okay, and the transformation parameters are xi a and xi alpha. Okay, now the Weyl-Bine transforms only under diffeomorphisms. Right, so the interior derivative is given like this. Okay, is this part clear? So this is just the fact that interior derivative of the Weyl-Bine will only contain the space-time part. Okay. Oh, sorry. What am I saying? Yeah. So Weyl-Bine only transforms under diffeomorphisms. Okay. And we know that this is the interior derivative on the Weyl-Bine. Okay. These are two things. Okay. On the Weyl-Bine. So this we know from before, right? This we know from earlier. Okay. Now interior derivative on A alpha can be defined as xi A alpha is equal to xi A alpha plus xi alpha. Okay. So this we know earlier. Okay. And we know that gauge transformation has no action on EA. So there is no need to generalize this one. Okay. Whereas the interior derivative of A alpha, okay, the first term is the fact that A alpha is a one form, right? So this is just a reflection of the fact that A alpha is a one form on space time. And for a one form, it is xi mu whatever, xi mu A mu, xi mu B mu whatever. So here it was xi mu E mu A, and here it is xi A alpha. And this is the natural generalization of this, okay, which is that EA, okay, is associated with the space-time diffeomorphisms, okay, and A alpha is associated with these xi alpha diffeomorphisms. Okay, so xi alpha should appear in the interior derivative of A alpha. Okay, is this clear? So we use this as a motivation. Okay, so interior derivative on any vector v mu is just xi mu v mu. Okay, so we use that to obtain I xi EA as xi A. Okay, and there is no need to generalize this because E mu A does not have any gauge direction. Okay, and you take I xi A alpha. Okay, and that has these this interior derivative. Is this okay? Okay.
Hello. Hi.
Hi.
So the A small a index is the tangent space index, right?
Yeah.
Okay. Thank you.
Okay. And also I have shared my notes. I think before about this. So if you want to follow like the previous slide, so maybe you can look at it. If I have not shared my notes, then I don't know, like I'm forgetting what it was, if I have shared it or not. So now what we know is that field strength F is defined as dA minus A wedge A, okay, for this gauge theory. So we will change dA to this, okay. So dA in the action we will replace by F plus A wedge A. And the reason for doing that is that this dA, okay, it is not clear what legs it has. I mean, does it have the Weyl-Bine Wellbines with it or in the Lagrangian, or does it have the gauge fields appearing with it in the Lagrangian? Okay, so let me just write it explicitly. So this is half F alpha AB EA wedge EB plus 1 over 2 F beta gamma alpha A beta. Okay. So here I had just hidden the structure constant, so which I am making apparent here. Okay, because once you took the gauge directions and took their wedge product, okay, so this is what you get. Okay, took that index out. Okay, this is what you get. So whenever I have dA alpha, okay, I will consider that it has EA indices and A indices. Okay, I mean, I don't know whether to call them indices. dA comes with EA Wellbine and A beta Wellbine. Okay, so this is how the super Wellbine will appear inside dA. Okay.
Sorry, this is my definition of PA.
Yeah. I mean, in the sense that so what we want to use is the feature of the super Wellbine, which appears on this side. Okay. Usually we use F, right, the left-hand side, to construct gauge invariant actions. Okay. But what we want to use is a different principle for which the super Wellbine is more useful. Okay. So whenever we have like, let's say Chern-Simons action, which contains dA, okay, we will just replace it by F plus A wedge. Okay. If we just had like, let's say F square action, then we would have no trouble. Like F just has the Wellbine, okay, appearing like 4 times. Okay. But what to do like in Chern-Simons theory, where you get ADA, okay, then we replace it by this formula.
Here in the right hand side, the EAs and EBs are the full super Wellbines.
No, EA and EB are the usual Wellbines. With the super Wellbines, we have the notation EA.
Oh, okay. Yeah, sure.
Okay. Yeah. Okay. So now, what we can do is that we can write gauge transformation on A alpha, okay, as d of ixi A alpha plus ixi d of A alpha.
Sorry, Subbu, small question. So have you already assumed that the object F that you have defined is a gauge invariant object?
Object F I have defined. Is a gauge invariant object. Not really, but yeah, I mean, it is true, but what is important for me is that it has this these indices, EA and EB.
Okay. Thank you.
Yeah. Okay. So we will soon see like what will become important for like the gauge invariance. Okay. So this can be written in this way, where we have said xi A20. Okay. This, if you just take both of these xi as xi alpha, then this gives you the gauge transformation. Okay. Yeah, I think Anish was right. So this is only the space-time covariant derivative, it seems like, exterior derivative, it seems like. Right?
Okay. Yeah, I think so too.
Yeah.
So, so then it is. Then I don't understand exactly how the Cartan formula applies. If I take a generic diffeomorphism that's supposed to include both gauge transformation and spacetime. So suppose you take a xi which is both spacetime diffeomorphism and gauge transformation. I take a xi that is diffeomorphism, but both of us will use the same formula that I find a bit confusing.
Yeah, actually what happens is that like we could have used the full structure, okay, but what happens is that ultimately when we take the action, on the action this d, how do I say it, action has like dx mu and so on, okay, and let's say it also has some gauge directions, right, like I don't know how to call them, so let's say theta alpha, theta 1 to d theta, the gauge group dimension.
Okay. Okay.
I mean, and some general combinations of these terms. Okay.
Right. Okay.
But when we ultimately write this action, it is evaluated over d theta is equal to 0.
Okay. Okay. Right.
So that is why even if you go to the full super covariant approach, okay, which will be like a super space like approach, okay, there you will do it more rigorously, which is why I was initially saying we are doing an abuse of notation. Okay. But ultimately, once you obtain the action, all these other terms will go to 0. Okay. And the term that you obtain initially will be the same. So.
Okay. So I mean,
for the space-time integral, the action will be the same.
Okay. So somehow you are already performing the integral over the other coordinates or something. Is that happening, or there is a constraint that those have to be 0? I mean,
we are keeping in mind that d thetas will be 0 eventually. Okay. So let me put it this way. Where am I not careful? I am careful in not dealing with exterior derivatives with d theta and so on, right?
Okay, right.
But whatever is that subtlety, d theta is 0 in the end anyway on what I am trying to evaluate. Okay. So that is why this does not become important.
I see.
Yeah. So we could take d thetas. Okay. But in the end, d thetas are set to 0 in the action. In the Lagrangian, right? And J is that object which I am trying to manipulate.
But suppose I have xi dot d theta type of a term such that it's no longer d of something. I mean,
no, whatever it is, all those directions are set to 0 in the action. It is only a pure integral over the space time, right? The action that we want.
Okay, so you're saying that it will. I mean, if you are more careful, those terms will still drop out at the end.
Yeah.
Okay.
Yeah. So in fact, this is the difference between super space covariant superform technique. Okay. For which one would have to go to conformal superspace, like developed by Daniel Butter. Okay. But in the component technique, one uses this abuse of notation. Okay. But one manages to find the Lagrangian. So that is the difference. Yeah.
Okay.
Yeah. Okay. So now let us evaluate dj. Okay. So dj will be given by d of the whole thing. Okay. D of trace ADA minus 2 by 3 A wedge A. Okay. And this one can write as trace of dA wedge dA minus 2 dA A, which I am sure like most of us have done this step when we did Chern-Simons theories. So this will give us trace F wedge F, right? But then you remember dA is F plus A wedge A, right? So that will give some F plus A wedge A term. So here also we will get, here also we use dA is equal to this, and here also we use dA is equal to that. Okay, and the final answer is given here. So let me copy paste this thing to the next. Okay, so this is what we get, right? So we apply d on this, d square is 0. Okay, and this d on all of these are same with so 3 goes away, and then we substituted d is equal to F plus A wedge A. Okay, and we obtain this. Okay, so now notice that this is a 4 form, okay, but it is a 4 form on the full ouch. Now this is a 4 form on the full manifold curly M, right? Therefore, it need not be 0. I mean, it's even though the space-time dimensions are 3, it's not like a 4 form in 3 dimensions, okay? But what we should note is that this thing has legs only along Weyl-Bine direction, right? The first term, because we saw here that F has this EA, EB, which is the Weyl-Bine direction. Okay? And if you write F wedge F, okay, that will be proportional to EA wedge EB, wedge EC, wedge ED. Okay? But now there are these space-time indices, right? And they run over only 3 values. Okay? So because this has only 3 values, okay, this is 0. Okay. Yeah. And the second term is 0, okay, because wedge product is antisymmetric, okay, but trace is cyclically symmetric, right? And you know that if I have antisymmetrization in 4 indices, right, any index, 4 index, okay, that can be, when you do cyclic permutation, it will reverse sign, okay, Lij. Okay. So under cyclic permutation, antisymmetrization of 4 objects will reverse sign, whereas trace won't reverse sign. Okay, therefore dj is 0. Okay, and that tells us that the non-abelian Chern-Simons gauge theory is gauge invariant. Is this okay?
Sorry. So, what is the problem saying that since we are working in 3 dimensions, a 4 form should not be there. So, it should be 0.
Yeah, but what I mean is, suppose we had E wedge A, right?
Mm-hmm.
Then this could be possible because there is ABC, right? And this has index alpha, right? This is a 4 form, but this is a 4 form defined on curly M, right?
Okay. Okay.
So this is possible, okay? Whereas this one is not possible, okay? So, and our evaluation gave this answer, which is not possible, okay? And that is why it is 0 and it is gauge invariant.
So it's not a top form in if you consider it.
Curly M, yeah.
Yeah.
It's not a top. Yeah. Okay. So now I will go to conformal supergravity. And in the next 20 minutes or so, we will derive the chiral density formula in conformal supergravity, okay, using this method. Okay. In conformal supergravity, one uses the same approach, okay, and defines a super Weyl-Bine, which has dx mu E mu A plus d theta m E m A, okay, and this EA, when you set theta is equal to d theta is equal to 0, we get EA half psi, okay, with opposite chiralities. Okay, what we are saying is that if you expand this, okay, it will also have d theta directions, okay, and also theta variables. If you set all of that to be 0, okay, then you get this as EA mu dx mu plus half psi I mu dx mu plus half psi I dx. Okay. This is the Weyl-Bine, super Weyl-Bine. Okay. So this is the abuse of notation that we are doing. Okay. So yeah.
Subbu?
Ha.
Can you just repeat the notation? Repeat the notation in the sense M is in this supersymmetric direction?
Yeah.
And how many? What does so M is the number of supersymmetry?
Yeah. Number of supersymmetries. I mean, you can think like 4 supersymmetries or whatever. Yeah.
I see. Okay. And what about conjugation?
Conjugation. What do you mean by conjugation? Oh, there is also E bar A. I won't write it. Yeah.
Yeah. That's what I meant. Okay. So there is a E bar that is included in this.
In this theta. Yeah. This M is sort of like a generalized direction, which has all this. Yeah.
It has everything. Okay.
Yeah.
Okay. Fine.
Okay. And what we know is that J is a 4 form in curly M, and it can be written as J DCBA, EA, EB, EC, ET. Okay. So we suppress the wedge product. Okay, from now on. So there is a wedge product between EA, EB, EC, ED, which we won't explicitly write. Okay. And what we are doing is, for example, J can be written as some J psi power 4, okay, with 4 psi terms. Okay, psi bar I, psi j, so on. Okay, they will be bilinears, but with a wedge product. Okay. And there might be 1 Weyl-Bine and 3 gravitinos. Okay, and then in this case, this will be a fermion. Okay, and this will have some bilinear with one of the terms. Okay, and the other terms will be the psi bar psi and E plus so on. Okay, so we can expand in this way. Okay, we can expand the terms in the number of gravitinos that they carry. Okay, and the Rheonomy principle tells us that there should only be psi and E mu A sitting outside. Okay, or any other gauge fields if they are there. Okay. Any other physical gauge fields of the theories that we are going to construct later. Okay. But from like superspace approach, this can be more evident that psi and E will appear. Is this clear so far? Okay.
The factor half is important, or is it just a convenience?
Oh, half is convenience. Actually, this half I never mentioned in these lectures. So usually, like in n is equal to 2 supergravity, when something transforms to let's say del q E mu A, okay,
right,
is okay, this was a bad example. So del q x, okay, was epsilon bar I d slash omega I in vector multiplet. Okay. So d mu x will have del mu x minus half psi bar mu I d slash omega I. So there is a half factor, which is a convention. So half psi mu is thought of as a gauge field. Okay.
Okay.
So therefore, del q psi mu I, instead of being d mu epsilon I, it will be 2 d mu epsilon.
I see. Okay.
I don't know why this convention, but this is the standard convention in n is equal to 2 supergravity.
I see. Okay.
Yeah.
Right.
Yeah. Okay. Yeah. Okay. So now what we will do is block by block, we will try to, block by block, that was a flop. Okay. Anyway, I'll just explain it here. Okay. So block by block, Okay, if you want, you can be rigorous. +1. So block by block, we will try to ensure that this is covariantly closed. Okay. So for this, okay, so what we will do is, first we will make an assumption, okay, that this block, or for example, JDBCA. Okay, I think I changed DCBA. Okay. EAEBECETA. We will assume that this is already covariant with respect to every transformation. Okay. Except Q and S. So C. Okay. The way to do that is when you try to construct a density formula, right? You begin with an object which is invariant under, which has Weyl weight 0, chiral weight 0, and so on, for example. Okay. Here it won't be 0. For example, if you start with psi bar psi, psi bar psi. Okay. If you have, let's say, psi bar I, psi j, psi bar k, psi l, epsilon ij, epsilon kl as j psi power 4, okay, and some composite, let's call it A. Okay, the wedge product is suppressed. Okay, and so if you check the chiral weight of all these fields, right? So you will see that all these have chiral weight half. Okay, so A should be covariant with chiral weight minus half. Okay, so this J, okay, it is invariant with respect to all the bosonic transformations, okay, by construction. The way we will ensure that is our beginning block. Okay, we will make sure that the beginning block has the appropriate Weyl weight and chiral weight. Okay, because this should have chiral weight 0. Okay, the total thing. Okay, because it is a part of the action. So we will make sure that this has appropriate chiral weight and Weyl weight, so that this has chiral weight 0 and Weyl weight 0. Okay, once you include the e to the power minus 1 that I ignored. Okay, so Weyl weight 0. So, and what you need to do is iteratively ensure that Q sub C, okay, is invariant. Okay, I'll just demonstrate how that happens. Okay, so what will be important for us is only this. Okay, del Q E mu A or del Q E A, okay, is epsilon bar I gamma A psi I, okay, plus Hermitian conjugate. Okay, so we will define something called as del A, which contains only this chirality thing. Okay, let's say. And that is minus psi bar I by 2 gamma A psi. Okay. And we will give it a notation. We will call it T0 acting on E. Okay. The other chirality, okay, so will be delta E is the other chirality. Okay. But we won't need that because they are related by Hermitian conjugation. So basically what I am trying to do is I am trying to see how, when we take the covariant derivative on all these fields, okay, we will get various terms. Okay. Yeah. And then you take delta psi I. Okay. Delta psi I will be, I'll just explain this and this might help to understand the equation above better. So basically, this is just like the thing we had earlier where dA was F plus A by J, where F is the curvature. Okay. So here also the same thing is happening. Okay, where we have delta on psi. Okay, which is the curvature times some other extra covariant term, okay, which came because of introduction of auxiliary fields in the multiplet. Okay, so what I'm trying to say is, if you take this to the left hand side, okay, that will give you expression for the curvature RQ. Okay, so we are just manipulating that. Okay, so this is also a part of the curvature of RP. Okay, this is just the torsion. Okay, and so on. Okay, so now what I am going to do is, so take this block A, okay, which we had in J psi power 4. A psi bar I, psi j, psi bar k, psi L, epsilon ij, epsilon k. First of all, whatever block you start with, it should be consistent under SU2 symmetry. For example, this is antisymmetric invariant tensor of SU2. And because of the wedge product, this is also antisymmetric, psi bar I, psi j, right? Because psi bar I, psi j, okay, is usually psi bar j, psi I. But now because of the wedge product, it is minus psi bar j, psi I. So that is consistent. Okay, so it is consistent under SU2. It is consistent under U1R because chiral weight becomes 0. It is consistent under Weyl weight because Weyl weight becomes 0. Okay, now the next step we need to do is take the transformation of A. How could it transform? Okay, it could transform as epsilon bar I times, let us say, some psi I, okay, plus epsilon bar I, okay, times, let's say, some lambda I. Okay, we will show that one of these will become 0, okay, just by this construction. Okay, and the way we will show is that, so let me copy paste this. And the way we will show this is that, take this transformation. Okay, let's say take delta QA is equal to epsilon bar I. I don't remember the notation, lambda. Oh, it's just above. Yeah, sorry. Okay. I'll just need 10 more minutes.
Yeah, you will have 5 minutes anyway.
Yeah. Delta A, okay, let's call it as psi bar I by 2 lambda. Okay. Basically, if you take the covariant derivative of A, okay, it will have all the covariantization with respect to B mu, with respect to other bosonic transformations, which is already here. Okay, so this is covariant with respect to all bosonic transformations. Okay. So the only thing we should make it covariant with respect to, which is left, is psi. Okay. So making this covariant with respect to bosonic transformation is useful, okay, because the starting block is already invariant under these transformations. So if you only use derivatives which are already covariant, okay, then you will, so every following block will also have invariance with respect to all the bosonic transformations. Okay. So now take this object and compute delta J psi power 4. Or maybe I will, this has to be minus, I guess. This is minus psi bar I. Okay, it is minus on the other side because that is the covariant derivative. Okay, so this is delta J psi power 4. Okay, so that is, let's take this term. Okay. Oh, this is a very bad notation. I'll call it phi I or something. Chi I. I'm so sorry. Actually, every letter is bad because it is some other field. We can't help. So let's take delta. So this is psi bar L, chi L by 2. Okay. Psi bar I, psi j, psi bar k, psi L, epsilon ij, epsilon. Okay, I should not have used L. Okay, these are just dummy indices. Okay. So now what I want to show is that take this object, okay, and consider and interchange chi bar, chi and psi. So by T0. Okay, so here there is no wedge product between the two. Wedge product is only between these four, right? Psi bar I, psi j, psi k, psi l. Okay. Did my screen freeze or is there a delay? Okay, now it is come. So take this and take, for example, psi bar I, psi j. Okay. Now what you do is, there is a delay.
So for the last 10 minutes, maybe you can keep the video off so that.
Oh, yeah, sure. Yeah. Okay. So now what we do is we do Fiersing between this. Okay. Psi m and psi bar m. But before that, notice that we have this Levi-Civita, epsilon I. Okay. And this is antisymmetric in I. And we can use the property that antisymmetrization of 3 indices in SU2 is 0. So I'm doing it on the right upper corner. So psi m epsilon ij total antisymmetrization is 0, identical. Okay, because I and j and m run over only 2 indices. Okay, whereas antisymmetrization is over 3 indices. So this will relate. Okay, if you expand this, it will relate psi m epsilon ij, which we already have. Okay, to, and there is some antisymmetric tensor aij, which is the psi bar I, psi j, to psi bar, let's say psi bar I or psi I epsilon jm. Okay, the signs might be off. There is still a delay. So basically, I am just trading these indices, okay, by using that antisymmetrization property. So I will have chi bar m, okay, psi I, psi bar I, psi j, epsilon jm. Okay. And if I do a Fiersing, this will become minus psi bar I, psi I. Okay, I'll just wait so that people can copy this. Okay, and I didn't. Okay. So what I did is I took the Fiers arrangement here, and since these are chiral spinors of opposite chirality, there is only one kind of term with gamma A and gamma A. Okay, so this is the Fiersing, and you can identify this as T0. Okay, on EA. And of course, the psi bar k, psi l is still hanging around here. Okay, so ultimately, what you get is delta j power 4, j psi power 4, okay, is delta EA, okay, and chi bar m gamma A psi n epsilon mn psi bar k psi l epsilon k. Okay, what this tells us is that we started with j psi power 4. Okay, but there is also, which has 4 psis. Okay, but there is also j e psi cube. Okay, which has 3 psis. Okay, which has this as a fermion times a psi and psi bar psi and an e. So what we did is we did delta on this. Okay, and the answer is of the form delta E, which is here. Okay, chi bar, okay, which is here, okay, times psi bar, psi, okay. So delta E is telling us that suppose you took a term of this form, okay, and did delta E there, okay, that term can cancel with this term and covariant closure can be satisfied, okay. So this tells us that J E psi cube will have this form, chi bar psi, psi bar psi. Now if you go to our chiral density formula, right, this is that term. This psi L is nothing but what I called as chi L, okay. And this is, if you see, this has 3 gravitinos, okay, and 1 Veblen in the place of this gamma matrix, okay. So what we obtained is that the first composite led to the second composite, okay. And the only extra thing that we need to know is that suppose we considered the opposite transformation, okay, which is let me call it as del bar psi J psi 4, where I would take del bar A, which is, so here I took, I'm sorry for so many, okay, so I'm calling this as delta A and this as delta bar A, okay, and maybe this I'll call as some delta half. So let me take delta bar A now. So first I considered this term, it gave me the future composite. If I take this term, right, then I would get half psi bar I upper lambda. Okay. Now notice that I already had psi bar I, psi j, psi bar k, psi l, epsilon ij, epsilon kl. Okay. And from this I will get psi bar m, lambda m by 2. Okay. There is nothing to cancel this. Okay, because if you go and look at the transformation of the Weyl multiplet, okay, and see like if there is any term in delta psi, okay, covariant derivative on psi, which has let's say 3 psis, okay, so that the cubic one can go to the quintic one, okay, which is what we are getting here, okay, like 5 gravity. There is no such term. Okay, that tells us that if we begin with this J psi power 4 term, okay, which has this form, if we begin with this term, then this transformation, right, it should not have any transformation of this form. Okay, this is 0. Okay, so lambda I is 0. And this tells us that the multiplet is chiral. Okay, so instead of beginning with the chiral multiplet, we begin with this J psi power 4 block. Okay, and we impose covariant closure block by block. Okay, and that tells us both what the next block should be and what should be the constraint on the transformation rule of this block. Okay, so if you keep on doing this, you will get the full density formula, okay, which is what we had here. Okay, so chiral density formula can also be derived this way, and this method was used to derive new density formula. Okay, let me just take 2 minutes to make some more comments, and then we can pause and take as many questions. So the only comment that I have is that even though one considers all these gravitino terms and so on, if somebody is considering only the bosonic sector of supergravity theory, okay, in this whole expansion, of J psi power 4, psi power 4, J E psi cube, and so on, the last term, okay, which has e to the power 4, that is the bosonic sector. I mean that has both bosonic and fermionic terms. Okay, so take that L and set fermions to 0. That will give you the bosonic sector action. So if you only want the bosonic sector action, you can aim so that you only get the bosonic part in this term. Okay, you don't need to compute all these composites to full effect. You can only compute them for enough number of fermions so that you get only the bosonic terms here. And that is important because in fermionic equations of motion, every term contains at least one fermion. Okay, so all fermions being set to 0 is always a solution to equations of motion. So this tells us that we can only study the solutions of the bosonic sector consistently, which is what many people do. Okay. Also for the fact that bosons are classical and there are bulk solutions. Okay. So if one is trying to construct only the bosonic sector action from supergravity, they can just do this. Okay. So I'll end here and people can ask questions.
Okay, I think before people can ask questions, Subbu, can you please turn on the video once again?
Yeah.
Okay. So I will request all of you to please unmute yourself and thank Subbu for this wonderful set of lectures. Okay, so we are running a bit late. People can ask questions, but I just want to point out that we will start the last lecture exactly at 4:30, so there will not be any delay. So if there are any pressing questions, please go ahead and ask. Otherwise, I will pause the video and you can ask offline.
Subbu, can you go to slide number 82?
82,
yeah. Just can you reiterate again the action of I zeta on A alpha, how you got the second term zeta alpha? And one more thing, so is this like sort of a definition or do you, I mean, you want sort of like Leibniz rule to be valid? I mean, I'm probably not phrasing it in the right way. Is that what gives rise to the zeta alpha term? Some sort of consistency of Leibniz rule?
Yeah, what I want is this thing in the box in the next slide. Okay.
Okay.
So when I set the space-time diffeomorphisms to 0, okay, I want the exterior derivative and interior derivative to act as Lie derivative to produce exactly the gauge transformation, okay, which was there given here. Okay. So how to realize this using generalized diffeomorphisms? Okay. That is the question. So if you want to do that, then this is one natural way you can think of, because what will this become? This will become Lie derivative, right? With respect to xi alpha, right? This delta G above will become L xi alpha, right? And this is a combination of interior and exterior derivatives, okay? And we need a suitable notion of interior and exterior derivatives, okay? So that this seems to be a natural notion, okay? Because A is anyhow already a one form on the space-time manifold, okay? And in the space-time manifold, for space-time diffeomorphisms, the corresponding gauge field had this kind of an interior derivative, okay? So for the gauge connection, okay, for the gauge transformation parameter, we are assigning a similar interior derivative, okay, so that the Lie derivative realizes gauge transformation.
Okay, yes, exactly. Yeah.
Okay.
Fine.
Yeah.
Okay, thank you.
And also what Anish asked was correct, like it was just the space-time exterior derivative, which is why we always have like the curvature and so on.
Okay, I think let us all thank Subbu once again.
Yeah.
So let me pause the recording. We will start exactly at 4:30 with the last lecture. Okay, so welcome back. We will have the first lecture on complexity in quantum field theory and holography starting today. And this topic, as you know, will be shared by 3 speakers. The first speaker in this course is Aranya Bhattacharya from SINP. Aranya, over to you.
So, thank you. I'd firstly like to thank the organizers for arranging this meeting and school and in this kind of time. And let's hope we stay safe and next year we can have this offline. So let me begin. So I'll be talking about complexity in QFT mostly. The holography part will be covered by Arpita, and a part of the QFT in complexity will also be covered by Pratik later. So let me briefly talk about the plan. Okay. So I'll give 3 lectures to start with, and if time permits, we have some time left at the end of 8 lectures, and if we have some time in the last lecture, I can come back and briefly discuss some other topics. But for these 3 lectures, in the first lecture, I will mostly talk about introductory things. It will be about the background and introduction. In the first half of the lecture, I'll be talking about mostly what does complexity mean in a classical computational perspective, and what does it mean in a quantum computational perspective, why quantum computational perspective is different from classical one and all. In the second half, I'll talk about sort of a calculation towards quantum computational complexity for qubits, n qubits. And at that point, I'll stop in this lecture. In lecture 2, I plan to talk about circuit complexity in free scalar field theories. And this is a big work and big paper, which I will be talking about, and it will take supposedly the full lecture, and it has mostly all the details that I want for the application part, which I will be talking about in the third lecture, in which I'll mostly concentrate on a different method of computing the same thing, which is covariance matrix method. Then for the free scalar field theories in the circuit complexity paper by Jefferson and Myers, they dealt with only pure state. So we will also know how to deal with in case of a mixed state. That's called complexity of purification. And finally, I will talk about how can complexity probe a quench dynamics in some system. So as I mentioned, the gravity side will be covered by Urpita, and the path integral complexity and its connection to tensor networks will be covered by Pratik. Primarily, it was planned that I will give the introductory lectures and then Urpita will take over for the gravity part, because to be chronological, the gravity came first in this picture of complexity. And then people tried to really match what was suggested to be the dual of complexity in the gravity picture. People started trying to define it in the quantum field theory picture as well, so that with the hope that one day we will also be we'll be able to exactly calculate this thing in the conformal field theory side. So let me start now with some background and introduction. So what do we mean by complexity? So it is basically, it basically means the difficulty of performing some, or rather difficulty measure of performing a given task. Now, when I say task, what is the task? Let's say a task can be of 2 types. One is classical, the other would be quantum. So for the classical thing, we would mostly understand these things from the point of view of a classical computer. So as we know, in case of a classical computer, the computer knows only binary things. So, and any job, if you talk about, it's defined in terms of binary string. For example, we can, let's say we are starting from a binary string of whatever number, let's say, let's fix some number, let's fix to length 6 binary string of this kind. and we want to reach to a state where we have some kind of this binary string. So the complexity is the difficulty measure of performing this task in case of classical scenario, whereas in quantum case, I'd say the automatic thing would be to say that we want to start from an initial quantum state and reach to some target quantum state. Now, while talking about quantum states, or the reference and the initial state is also termed as reference state. And so what kind of quantum states we will be dealing with? Since the motivation came in the picture from the holography side or from the ADS black hole side, the ideal situation would be to deal with CFT states. But of course, CFT states are not easy to start with. So the ideal point to start from is qubit systems. And once we understand this thing, then we'll go to a QFT scenario. Okay, so I have mentioned that we want to implement this task or this given task, but we would need some, of course, some machinery to perform this task. So what would be the machinery? The machinery would be gates. Now, okay, should I stay in the slide? I don't think so. Okay. So if we talk about gates or the task itself, then let us think about the classical computer as a, let's say, a combination of wires. A computer we would call a combination of wires carrying information. And we would call the gates as some instruments that modifies this information. And if we have a reference state and a target state in mind, we want to modify the information in a particular way. Okay, so in case of classical computational complexity, what would be the measure of difficulty then? Classical computational complexity, or rather it will be the same thing in case of quantum version as well. So we want to have this measure as let's say the minimal or rather optimal number of gates needed to perform this task. And this combination of gates that would typically perform or implement this task is known as, in computer science language, combination of gates is known as algorithm. So when we say that we want to compute the optimal number of gates needed to perform this given task, or we want to compute the optimal algorithm, then there are different conditions we can talk about. For example, how do you define optimal? So optimal can be defined in two ways. Although here I have mentioned that optimal number of gates, I have specified the way I want to measure this, but it can be of two ways. One way would be to minimize the number of gates, which I have mentioned. And the other way could be minimize the time needed. And these two conditions are optimal conditions, rather. Are sort of, they always don't lie in the same line. That means we can have a minimized number of gate situation where the time needed is huge, and we can have a minimize the time needed situation where we have to at a time we have to introduce so many gates that would change the rate of introducing new gates. So but the problem that we'll be concerned with is the first one, that is minimizing the number of gates. And as you will see later, that the time coordinate will be kept sort of the initial to final time will be always considered as some normalized version as 1 or something. So we won't measure the final time coordinate in that way. Okay, so let us talk a little bit about classical gates. We already know about these things from our BSc days or whatever. So the classical gates can be of two types. One would be a single gate, single beat gate, and other would be multiple. So for the a single bit gate will at a time act on a single string of a binary string of length n or l, whatever. So it acts on a single number 0 or 1, whatever is there at particular number. Say we have a string of 1 1 0 0 1 1. We can act with this single bit classical gate on this one or this one, but not at a time on more than one bit. And a multiple bit will gate will act on multiple of these bits at a time. It can be these two, these two, these two, and it can be these two as well. So what are the we know actually we know a single choice of single bit classical gate. Which is not. So this takes 0 to 1 and 1 to 0, vice versa. So, and a multiple bit gate, we know a few of them, which are say and, or, nor, zor, etc. Now, there are once when we will be talking about the quantum gates, we will see that there is a difference between classical and quantum gates. So the classical gates, if you leave out not gate, the single bit one, this is okay. I think I'm online and my iPad has been offline. So I have to re-log in. Okay, sorry for the interruption. And okay, so once we will get into quantum gate situation, we will see that there is a difference. Let me talk about it at this point already, that instead of not gate, the multiple gates are irreversible. That is, they are not invertible, or from the output of these gates, we cannot really guess, or by operating it on the output, we cannot get back the input states, or we cannot specify the input states. And this is called in the classical computer science as some information loss, although this is very much different from the information loss that we talk about in holography or gravity. So the next thing that I want to talk about is universality. So this is to mention what we want to talk about actually is sort of universal gates. And this means that some set of gates for which using those this set of gates, I can implement any function or action in a scenario. So for example, what turns out is in case of classical computer science or classical computational complexity, the universal set of gate can be thought of as a single NAND gate, because using NAND gates, you can, using this, any other gate can be. So we can make any other gates present in this classical set of gates using just a single gate, which is NAND gate. So typically people call that NAND gate is the universal classical gate. So before moving to quantum gates and quantum mechanical situation, let's talk a little bit about the Turing machine, which is typically what people call is the first computer. So the idea of Turing machine is it's of course was invented by Alan Turing, and he named it a machine, which means automatic machine. And so the idea of this machine is to this is a machine with a with a given set of basic instructions. It can perform or rather solve any given problem. So given set of basic instructions, it can solve and with time actually this definition kept changing. So there has always been this great debate in computer science that people try to come up with new problems which they say that the Turing machine cannot really solve, and then some modification in the Turing machine again does the job, and it actually is again able to solve the new problem at most of the times. So there is something called which is again this kind of statement, which is called strong charge Turing thesis. And what this says is that any algorithmic process can be simulated by a probabilistic Turing machine efficiently. Now this efficiently actually means something very tricky in computer science, but this has mostly to do with this efficiently term, has mostly to do with the resources, number of resources rather. And again, the time needed. So again, we can see that this point of efficiency again brings us back to the optimal definition of complexity. So by computing, yeah.
I have a question.
Yeah.
Yeah, so this definition of Turing machine that you said, that given a set of basic instructions, it can solve any problem.
Yeah.
So isn't it in contradiction with Gödel's incompleteness theorem? Because if I give it, say, suppose axioms which are sort of Zimmerle-Frankel axioms, then if I ask it to prove a Gödel statement, then it should not be able to prove it.
To be honest, I don't exactly know about this problem that you are mentioning, but
so okay, so Subramanya, maybe I can make a comment.
Yeah.
So there is an equivalent of that statement for Turing machine called as the halting problem.
Yeah, I know.
So any Turing machine cannot solve its own halting problem. So, but I think.
Yeah, that's why, I mean, the statement that it can solve any problem, I have a problem with that statement.
Like whatever is computable will be computed by the Turing machine.
Yeah, I mean, I think the correct statement should be that it can solve any problem which is not a Gödel statement of the basic instructions given to it.
Yeah.
Okay. Yeah, please continue.
Yeah.
Sorry. What do you mean by a probabilistic Turing machine? I mean, where exactly are you attaching the probabilities to?
So again, this came as a modification in this Turing machine thesis, strong charge Turing thesis. Primarily, it was termed as any algorithmic process, just any algorithmic process can be simulated by a Turing machine. But this probabilistic Turing machine came into the picture when there were some problems that were suggested by, at different times, there were some problems that were suggested by different computer scientists, which and they claimed that these problems cannot be solved by the primarily defined Turing machine. But that's what I said, and that I will be actually I'll not be talking about this much.
Can I make a
modification
comment on that
came
also?
Yeah, sure.
Okay, so basically probability is introduced in the sense that probabilistic Turing machine will give you the right answer with some probability, like two-thirds of the probability. And if that is like admitted, then you can make like algorithms much more efficient. So it can solve bigger class of problems than the usual Turing machine. So that's why probabilistic Turing machine is used.
I think it also takes into consideration. Yeah, sorry.
No, the reason for asking was this is like the strong church Turing thesis is not some sort of quantization or anything of.
It's classical probability.
Yeah.
Classical
probability.
This is also classical. Okay.
And it's about taking into consideration some kind of classical noise.
Nishant has a question. Please go ahead.
So I have two questions. So you are talking.
Nishant, can you speak a bit loudly?
Yeah. Can you hear me now?
Better, but if you can speak a bit louder, it will be even better.
Okay. All right. So I was saying that you are talking about the problems. So I'm not able to understand. Can you give me an example of like the sort of problems that this Turing machine can solve, like the complex sort of problems, like one that would require a probabilistic approach? Like just like you said that there were like computer scientists who had to implement probabilistic nature because some sort of problems were like proposed. And I'm not able to like understand what sort of problems are we talking about here. Can you just give one or two examples of that so that I have like.
Yeah. So the problems that I'm talking about is primarily the problems that, of course, the Turing machine was made to deal with was the any kind of given thing that we problem that we try to solve in a computer, or even whatever you solve in hand, the computer should be able to solve it given a few set of basic instructions, which are kind of equivalent to giving some boundary conditions in some cases, and so on. But the other problems is, one of the problems I know about is the prime factorization problem. So given a any what can be the largest prime number that mathematicians talk about, is can it solve the problem? That is an unsolvable problem, if I know rightly. And
Okay, and can you also comment on this, like what problem led to this probabilistic, this Turing machine, the concept of probabilistic Turing machine? What sort of problem was that? Like, do you have any idea about that?
okay, so actually I can try to look more into it and talk about it, but my primary motto in talking about this was not to really get into the
Oh,
Turing
okay,
machine
okay.
scenario. So
Yeah, yeah.
maybe I can
Yeah, yeah, okay, okay. Got it.
comment on it
Thank
later.
you. Yeah, next.
Vinay has a question. Vinay, go ahead.
Aranya, I
Yeah.
had a question regarding slightly earlier slide.
Yeah.
You said the optimal way of doing algorithm, you can either characterize it by number of gates or time, right?
Yeah.
But
Yes.
if we decide on some basic gates, then won't the time depend on the number of gates?
No,
Realistically speaking.
that's the point. I thought I would come back later. So if you are given, before you start doing the operation, if you are given a set of universal gates and you are ready with them and to perform the task, and you know that you can perform any task with them, then it should not really matter how much time you need. But if you are not given if you don't strictly have a universal set of gates, then you'd have to keep in consideration the amount of time needed as well. So yeah, but you can also think about this in this way, that even if you have a universal set of gate and say you have to use, say, 10 of the first kind of gate, 20 of the second kind of gate, and at each time you can use a single gate from that case, or in a unit time you can use only one gate, then actually these two situations can also be the same, that the unit time equals to unit gate. In that scenario, minimized number of gates and minimized the time needed would be equivalent to each other. So you can think about this problem in different ways. Okay, so should I? Yeah. Okay. Yeah, so finally, again, for example, when I told efficiently, what in the later picture came in front of us is once people tried to use the ideas of quantum mechanics into a classical computer, these definitions of efficiency again broke down. So you cannot really do some quantum task or quantum mechanical task efficiently in a classical computer or a classical Turing machine. But again, if you input the postulates of quantum mechanics as the basic instructions given to the Turing machine, or rather what people talk about when people talk about quantum computers. That is what people mean, is that you give as the basic instructions, you also give the quantum mechanical postulates in the Turing machine. So you form sort of quantum Turing machine or a quantum computer. Then you can indeed perform the quantum mechanical tasks efficiently as well. So now, having this said this, let's get into the quantum computation or the quantum situation. Again, the quantum computational complexity means simply the minimal optimal number of gates needed to perform a task. But as we know that why is quantum computer special, that when we talked about classical bit, it was 0 and 1. There were only two possibilities. And if you had a, say, n length string or binary string, then the only things that you needed to know are whether at kth position, what is the number associated, whether it is 1 or 0. So you need to know n such coefficients, if I say. Now in case of qubit, what we call our qubits, if we have similarly two, say, possible basis states, and we can make one qubit state can be any of these, alpha 0 plus beta 1, where mod of alpha square plus mod of beta square has to be 1 to preserve the norm of the state. And so it's just not the 0 and 1 state, but all possible two tuple of this sort, which satisfies this relation, can be called a single qubit or one qubit state. And similar to n length string, if you want to go to some n qubit scenario, the way to go there is simply you take a, rather say I would, let's call the 2 qubit state as psi2. Then in terms of the basis states, we should be able to write it as some 0 0 plus 0 1 plus say 1 0, where these states are simply tensor products of two 0 states at two positions. But what we see is, in case of classical binary string, we needed to know about n positions or n coefficients. But in case of an n qubit scenario, to specify a state exactly, we need to know 2 to the power n such coefficients are needed to exactly specify the states. And again, so now knowing this, we can now talk about quantum gates. So again, in case of quantum gates, you would have single qubit gates, or we can have multiple qubit gates. A single qubit gate would, given for example this 2 qubit state, a single qubit gate would only act on this qubit, the first qubit of each state. And all of these states, I forgot to mention that all of these states, 0, 1, or whatever.
Aranya?
Yeah.
Yeah, Tushar is saying that shouldn't it be 2 to the power n minus 1 if we consider normalized states? And Subbu is correcting it to 2 to the power n minus 1. Tushar, do you want to unmute yourself and ask it?
Yeah, that was just my question. Like, it's 2 to the power n minus 1, or as he pointed out?
Yeah. I was just making the analog clear, but if you take into consideration the normalizing condition or alpha mod of alpha is square equals to 1, you can get rid of one of them, then you have 2 to the power n minus 1. Yeah, that's fine. You're right. But there are, let me say it in this way, what I wanted to say is that we would have 2 to the power n such coefficients. One of them, it's not really, this was a wrong statement. So we don't really need all of them to specify them. Using the normalization condition, we can get rid of one of them. But there would be 2 to the power n such coefficients. It's fixed this statement. That's what I wanted to say. Yeah. Okay, so, and as I was saying, so all of these states are orthonormal. So they are orthogonal to each other. These are sort of basis states of a 2 qubit scenario. So let's talk about the single qubit gate first. Now, if we say represent this state in this way, simply by writing alpha beta, then our single qubit gates would be 2 cross 2 linear matrices, but they have to also be unitary since we are dealing with quantum mechanics.
We want this to be a two-state system.
Sorry?
Is it much more complex to have a three-state system or a four-state system?
No, it's not much complicated. You would simply have, let's say, 3-fold tensor product or 4 tensor product of such state. You could have this one that would have again 2 to the power 4 such coefficients, and out of which you can, using the normalization condition, you can again get rid of one of them, and you can specify the state through these number of coefficients.
For a single qubit, why don't we have 0, 1, 2, for example?
0, 1, 2, I am considering similar to the, for example, binary situation. I am trying to consider a situation where I have only 2 basis states, or there are 2 possible eigenvalues that you have for a operator. For a state or an eigenstate of an some operator, you have 2 possible eigenvalues only. And that also goes well with, because I have written this, you can go to any 0, 1, 2 situation by some making some other scenario, so, but that would probably not be in line with the linear algebra methods or the matrices that we are using here. It would be easier to deal with the situation if you use this 2 qubit or 2 possible eigenstate situation. Then we can easily write these things in terms of unitary matrices, or easily understandable. Otherwise, you could have also, I think, other situations.
Subbu, go ahead.
Yeah, so I just wanted to point out that if you have three states, it's called as a qubit system, and similarly there are qubit system.
Yeah.
And linear algebra techniques do apply here. It's just that it will be a three-level system. But qubit computation is much less understood because quantum computational advantages are different from qubits to qubit and qubit. So people usually consider qubits as a simple example, and that is the most widely used in quantum information. But I mean, it's fine as an example. I'm just saying that even for qubits, one could use linear algebra.
Yeah. So for the qubit model is probably the holographic error correcting codes model. It deals with qubit scenario.
I see. Yeah, I don't know that. I mean, I
Okay.
just know that in quantum information they are there, but they are less well
Yeah. They are simply a qubit scenario would be the easier way to say it. You have three possible eigenstates or
That's it.
three possible eigenvalues.
And linear algebra applies. Yeah, I just wanted to.
Yeah. But you would have to model it in a different way, I would say.
Yes.
Yeah.
I don't know. I have a question.
Yeah.
So as you have said, while defining a single bit for classical gates, you said that there is only one choice. So only a NOT gate, like 0 to 1. Right?
Yeah.
So similarly here, are you also excluding 1001 matrix? I mean, identity matrix. You are not considering identity matrix as a single qubit gate.
Yeah. Identity matrix is not considered as a. It is a trivial gate, but whichever gate we will.
Yeah, that's fine. I just want to make sure. Okay.
Yeah.
That's not a single qubit gate. That's what you would call it.
You can use it as, but it would not lie into the say universal gate set of single qubit gates or whatever. If when you want to talk about identity gate is a trivial gate, it doesn't change in that way the state at all. So whenever if you want to get to some other state starting from somewhere else, you are really talking about the number of non-trivial gates that you need. Identity gate would not be counted in there.
Okay. I'm just comparing with the classical case. So in that case, you excluded identity.
Yeah, but there was also not identity gate, right? Identity gate was also.
Yeah. That's why I just want to make sure that here also you are not considering that.
No. Yeah. So, but unlike the classical scenario, there can be more than one non-trivial single qubit gates. So for example, to begin with, let's talk about the quantum NOT gate. And this should really change the 0 coefficient to 1 coefficient and 1 coefficient to the 0 coefficient. So we want a matrix representation of a quantum NOT gate which would take alpha beta to beta alpha. And the trivial state that does it is simply 0 1. This, if you apply this 2x2 matrix, it will take alpha beta to beta alpha. So this is the quantum version of the NOT gate. But this is not the only single or non-trivial single qubit gate. So what are the else? What are the other ones? There is something called Z gate. So let's say, I forgot to mention, let's mark this as this. Thanks. Okay, it has again gone offline.
Aranya, your iPad is not syncing with us.
No, actually, it gets offline in every 30 minutes or so.
Oh, I see.
Yeah. So let's call this X gate or the quantum NOT gate, denote this as X, and let's have another Z gate, another single qubit gate, which is non-trivial, and we'll write it as this matrix 1 0 0 minus 1. So if you act on this alpha beta, you would see that it always keeps the zero coefficient. So alpha is always unchanged, but beta is taken to minus beta. So what you have is it keeps zero unchanged and flips the sign of this thing. So it would take alpha 0 plus beta 1 to alpha 0 minus beta 1, which is also a valid qubit state. It's mod of beta, mod of alpha square plus beta square is still 1. So this is the second gate that I wanted to talk about. And finally, there's something called this is called Hadamard gate, or it is also sometimes called square root NOT gate. So the representation is simply 1 1 1 minus 1, and what this does is this takes 0 to so the act when it acts, it takes both 0 and 1 somewhere halfway between 0 and 1. And that's why it's called square root NOT gate, but it has nothing to actually do with, so you would not get actually, if you take a square of h, you are not going to get the NOT gate or the quantum NOT gate, but you are going to get h square equals to I. So the reason of calling it the square root NOT gate is that it takes the both 0 and 1 state to a place which is sort of halfway between 0 and 1.
So
and these are
the coefficients are not complex numbers, they're real numbers.
Yeah. They're always real. You could, in principle, no, you could have a phase, but I don't think, because if any one of them is complex, let me see. You could have in principle complex states as well. I mean, you could have an I in here, but let's say we are not dealing with such states here. In principle, you could have a state. As far as it satisfies this condition. So these are the three possible 1-bit or single qubit gates, and or non-trivial single qubit gates. And now let me talk a bit about a multiple qubit gate. We will actually deal with a single example of this, which is called the C0 gate. And what it does, it actually is a 2-qubit gate. which has, so it acts on 2 qubits. One of them is called control qubit. The other one is called target qubit. So let's say we would have a representation of C0 gate for which for a 2 qubit scenario where we have, say, ij, where ij both can be 0 or 1. In such a situation, we want to have a representation of C0 gate for which the first qubit is the control qubit, and the second one is a target qubit. So in this case, the way C0 gate is defined is it keeps the control qubit unchanged, and depending upon what is the control qubit, it either flips or keeps unchanged the target qubit. So if the control qubit is 0, then it keeps the target qubit, let's call actually C. Let's call the control qubit C and the target qubit T. So if C is 0, T remains unchanged. But if C is 1, then T is flipped. So here by flipping, I mean, if it was 1, it goes to 0. If it was 0, it goes to 1. So it's not flipping sign, it's flipping the state that I'm talking about. So what would be, let me write the representation of the C0 gate. So of course, since we are talking about a 2 qubit state, the vector that would represent should have 4 coefficients, and it should be say alpha, beta, gamma, delta. We would represent it through this 4 coefficients. And so our 2 qubit gate should have a 4x4 matrix representation. And the way I talked about that is if the first qubit is the control qubit and the second qubit is the target qubit, then the C0 gate representation is the following. So this part keeps the first qubit unchanged, the coefficients of the first qubit unchanged. And this part changes this. This part changes this coefficient of if the first qubit is 1, then it should change. If you can simply take it as an exercise and see that if you have, say, the control qubit 0, then your state would be 1, 0, and you could have anything in the target qubit. Let's say we have 1 state, then it would be 0, 1. Then if you act with this thing, you would simply get, so your control qubit is 0, and you should have your target qubit should remain unchanged. But if you had, say, your target, let's say, the control qubit was 1, then whatever state you would have here, the target qubit coefficients, that would be flipped. It was 0, if it was 0, 1 to start with, it would be 1, 0, and vice versa, if you act with C0 gate on it. So this 2 qubit gate is sort of entangling gate. since it acts on the second qubit, depending upon, or it depends upon what the first qubit state is. So depending upon what the first qubit state is in, it acts on the second qubit state, and therefore it entangles the two qubits in a way, or this gate quantum two qubit gate entangles the two qubits. But you can
Sorry,
also,
I have a question.
Yeah.
It's probably, I'm not understanding the notation,
Yeah.
but this state vector that you've written, for instance, in the first example, 1001,
yeah,
isn't the last one coefficient of the state 1 cross 1?
so one, what do you mean by 1 cross 1?
Sorry, so can you just tell me how this state vector is?
Okay. Let's say we have a 0, 0 state. So the first qubit is 0, and so is the second qubit. Then it would simply be 1, 0, 1, 0.
Okay.
Sir, it seems
Actually, I find it very. Oh, sorry.
it seems to be flipped in both cases.
Sorry?
It seems to be flipped in both cases, right? See the dependence on the first two coefficients.
You can check it actually. So let me write this state. I'm not sure whether I wrote it.
Can I make a comment?
Yeah, sure.
The way you wrote it, it will get very confusing for 3 qubits because the gates will be 8 cross 8. Okay? Whereas the way you are writing the column vector, it will only have 6 entries. Okay? So I think the right way to write it is like even for 2 qubits, the first entry will be 0, 0, second is 0, 1, third is 1, 0, fourth is 1, 1. So if you now write like 0, 0, 0, 1 in the LHS, that will go to 0, 0, 1, 0. So 1, 0 will go to 1, 1.
Yeah. So what you're saying is, say, I simply write it in this way, A00 alpha 00 plus beta. Actually, probably I messed up a little bit. I should have written that way.
Yeah, alpha, beta, gamma, delta are the column entries. Otherwise, at 3 qubits, it will fail the process.
Yeah. So the 00 state should be written in this way. The 01 state should be written in this way. The 10 state should be written in this way, and so on.
I think in this basis, the C0, the expression for C0 is.
I think I messed up. Yeah,
Pratik, you have your hand raised. Please go ahead.
Yes. So actually, this is now is correct because whatever in n qubit cases, you just have a tensor product for zero for the basis representation. You take 0 as 1, 1, 0, and 1 as a 0, 1, and then you can get n qubit representation just for doing the tensor product. So this is just a tensor product of four cases.
Yeah. Okay. So as I already told, I hope the C0 gate action of the C0 gate is clear now. So it entangles the two qubits. Depending upon the what the first qubit is, it can change or keep unchanged the second qubit. Now, as I told that when we are only going to deal with a single, only one 2 qubit state. The reason of this is, again, actually it's twofold. The first is that if we want to represent, or if we want to calculate the complexity of some n qubit scenario where we start from an n qubit initial state and we reach to a final n qubit final state, then if we could use arbitrary local, so this 2 qubit or n qubit, whatever number of qubit at a time the gate acts on, it is also called 2 local. So if we act with n local complicated enough quantum gate, then we could always get the complexity for any state to be 1. Since they are unitary matrices, we could multiply all of them and we would just get the complexity or the number of gates to be 1. So what we want to fix is a universal set of gates. And to simplify the situation, we want to deal with gates up to a 2-qubit situation only. So we will take 2 local gates as sort of upper bound. And yeah. In this regard, what Solovay and Kitaev showed, I'm just going to state this thing. This paper is, I have not gone through and I don't know the details about this paper, but what similar to the classical situation, what they claim is that for the qubits, any multiple qubit gates can be formed just by using the single qubit gates and a single or by a and only one entangling to qubit gate. So what Solovay and Kitaev claim is that any multiple qubit gate can be formed by these about previously mentioned 3 single qubit gates, and actually what they mentioned is these 3 single qubit gates and the C0 can form any other multiple qubit gate, and so we'll consider this set of X, Z, H, and C0 to be the universal set of gates. Okay.
Sorry, Aranya, can you repeat, please?
Yeah.
Why are you calling that entangling 2-qubit gate?
I'm calling it or the C0 gate as entangling gate because depending upon what is the first qubit, the C0 gate changes the state of the second qubit, right?
And does this not happen for other gates?
No. Since now we have only dealt with a single, only one 2-qubit gate, right?
Mm-hmm.
So we haven't dealt with any other 2-qubit gates. You could always have representations of 2-qubit gates which doesn't entangle the 2 qubits. So yeah, so you could have representations of 2-qubit gates which do not entangle the 2 qubits, but we want as a in the universal gate set, we necessarily lead whenever we go to 2-qubit gates, only then the point of entanglement comes in. And so we want to, otherwise if you would have the non-entangling 2-qubit gates, you could represent them just by using the single qubit gates as well. But any non-entangling 2-qubit gate, you should have one in your gate set because it's non-trivial. the single qubit gates could form any other non-entangling 2 qubit gates, but you need one entangling 2 qubit gate in your universal gate set. So you'd consider C0 to be that entangling qubit gate. But actually, this will not come in our next part of the lecture as well. But just to be precise, that for say we want to deal with n qubit situation, but we want to, so there can be interactions or entanglements between, we will only deal with entanglements between 2 of them at a time, and any other multiple qubit gate can also be formed since by using, as claimed by Solova and Kitaev, can be formed by using the single qubit gates and the single 2 qubit entangling gate. So we should be able to form any such gates up, keeping the upper bound of 2 qubit gates.
Subbu, go ahead.
Okay, so I have 2 comments. So one thing is just saying this differently, which is that you could have a 2 qubit gate, which is just a tensor product of 2 single qubit gates. Okay,
yeah.
So that wouldn't entangle the qubits. So that is not a genuinely 2 qubit gate. So that won't do. So we need a genuine 2 qubit gate. So another thing is that this said, so the actual solvative theorem is that you need all the U1 gates and C0, then you can exactly perform any quantum operation. And if you have this subset X, Z, H, and C0, then you can perform any operation up to arbitrary accuracy. Like you specify an accuracy, okay? Up to that accuracy, you can find some combination of them, some array of them. Okay, for some higher accuracy, you need some other array of them. I don't know if it's relevant later, but I just wanted to make this comment.
Yeah.
Prateek, go ahead.
Yes, this is actually will be relevant later, because this is the very heart of quantum computation, where the tolerance comes into the picture. Actually, because this is the, I mean, this Solova-Kitaev theorem is the most I mean, the heart of the quantum computation, where this epsilon comes into the picture. You cannot actually arbitrarily approximate a quantum operation. That is precisely what Solova-Kitaev actually states. So you need to introduce some accuracy for any real or practical implementation. I mean, so introduce some error tolerance, and that has
only
been
reach
introduced.
a state. Yeah. Sorry.
Yes, I mean, so precisely this theorem actually introduces a tolerance in your computation.
Yeah. So using this, you can say you want to reach some psi target from some psi reference. You could say that the norm of psi target minus whatever, let's say the combination of gates used to reach arbitrarily near the psi t states that we have used is, say, u psi er. This has all the gates that we have used in it, in the circuit. Then the norm would simply be, this would be less than some number. And this is what's called the tolerance of the circuit. So depending upon how do you define this, you could have different choices of other gates.
I have a question.
Yeah.
So classically there are these multiple bit gates, right? That will take, say, for instance, so all these AND gates or OR gates, they'll take 2 inputs and give you 1 output. Right?
Yeah.
So there are no quantum versions of these sort of gates.
I think you would have, but they would be just other versions of entangling gates. Say.
Oh, okay.
I just want to make a comment. So these are non-reversible gates, right? So in classical computation.
Yes.
So in quantum computation, every gate is reversible unless you like decide to throw away a qubit or something.
Yeah, since you are unitary gates as the candidates of your quantum gate, so it has to be invertible and as well as reversible. That would be.
Arnav has a question. Arnav.
Classically, why are you calling that is these gates are irreversible? Because I thought that the matrices that you are using are still unitary matrices. So cannot you bring back to the
No. What Subbu mentioned or Subbu meant was that the classical gates or the NOT, NAND, and those gates are, if you look at the Boolean algebras of those gates, that you cannot get back the inputs by acting something, inputs exactly by acting something on the output. But in case of any quantum gate, you have a unitary representation. So all of them are always invertible as well as reversible. They mean the same thing.
So classically, these matrices are not unitary matrices. Am I missing something?
You don't have a necessarily this kind of matrix representation in case of classical gates. You have a Boolean algebra sort of a thing, right?
Okay.
These representations are only for unitary matrices which act on some other linear algebra setting of representation when you represent the quantum states in terms of vectors. Then you act on those vectors using these unitary matrices. So since in quantum mechanics you expect unitarity, then thus your quantum gates are also typically unitary. But there will be some situations where there might be maybe you should use some non-unitary gates, but even then people sideline that or that do that in a different way by using some new qubits in the system, which are called ancilla systems. So for example, the trace, taking a trace of like taking a reduced density matrix from a density matrix, if you are going to a mixed reduced density matrix, that operation is a non-unitary operation. So whatever complexity primarily we are going to talk about is for pure states, and in the third lecture only I will come to the mixed state scenario where you have to compute for the complexity for mixed states or a density matrix situation where you don't have any vector representation, but all you have is a density matrix representation. There you the only thing you can do is to purify that density matrix to a pure state, and among all possible such pure states that you could form, you want to get to a pure state where the complexity is minimized.
Pratik, go ahead.
Yes, so I'd like to make a comment on this tolerance. Actually, Shubhamda asked in the chat, so I'd like to clarify a bit because this is going to play in later talks. So this tolerance actually in quantum computation, you do not put it by hand. It's actually inbuilt in your theory because you cannot approximate your state arbitrary accuracy. So that's why the epsilon comes. For example, in in lattice case, you can compare it with the lattice regulations. I mean this epsilon, this lattice spacing, it cannot go beyond this epsilon. In the continuum case, on the other hand, in a continuum case, you do not have a inbuilt cutoff in your theory. So you put it something some cutoff by hand. That's why you require some of your correlation functions or something to be that cutoff independent. So in the continuum, in the lattice case and this quantum computation case, this is epsilon is actually is in a theory, but in continuum case is not in your theory. You put it by hand. So I just want to make this comment.
Nirmala has a comment or a question on the chat section that he's asking that isn't x equals to h z h or the other way around?
Okay, I haven't checked that. I could check that and talk about it later after the talk. Maybe.
Yeah, sure. You can use the Slack to give the answers there.
Yeah, sure. So now let's talk. Okay, is this? Shit. I don't think the battery is down yet. So yeah. So let us discuss a little bit, although I'm not going to talk about it much since Urpitadi is going to, Urpitadi's topic is going to be solely this. And so the story of how this complexity came into holography. So basically what happened is, so let me, yeah. So what people observed is entanglement entropy could only probe a system up to thermalization, or up to a point when the system thermalizes, the entanglement entropy grows. That's what people observed both in case of usual quantum mechanical systems or in case of holographic systems where the holographic entanglement entropy formula was used. So in both of those cases, entanglement entropy saturates when the system thermalizes. But what Nielsen found in some of his works is that the complexity that he was trying to compute for an n-qubit system in such a scenario, the complexity keeps growing with time, even after my pencil keeps getting thermalization. Some part of the yeah, and so this interested Susskind, since when dealing with the black holes or the thermophile double states, what he observed was that for a two-sided ADS black hole, if you consider the time slices, let me draw the diagram. If you take a time slice that asymptotes in the two boundaries, these are the boundaries at some TL and TR. And if you keep evolving it with time, this slice that connects which is in the black hole region, which people behind horizon, which people also call the wormhole. So this is what people mean by the wormhole size. This part of the, as I told, I'm not going to talk at all much about it, but the size of this wormhole, what he saw is keeps growing even after the thermalization time scale, or rather to be precise, even after when entanglement entropy stops growing. So his motivation, what he suggested was the growth of this wormhole should correspond to something different than entanglement entropy in the boundary theory. And his suggestion was that this was dual to the circuit complexity or complexity of the dual safeties. So, but to really so he also considered he considered two things. Either you have to get the maximal volume slice and compute the spacetime volume of this wormhole, or you can, what you can do is take this whole slice and take the causal patch of that. Let me mark it maybe by another color. For this slice, you have to take this region and compute action in this patch, which is typically called Wheeler-DeWitt patch. So these are the two things that he describes as the CV, that is complexity equals volume and complexity equals action conjectures, which will be talked later about by Orpita Di in details. So what motivated the field theorist or the people who are now dealing with the circuit complexity in field theory was to really check whether at all this thing or these volumes or actions are dual to the usual notions of complexity of a field theory point of view. So the primary direction would be, of course, to go start from a free scalar QFT or free bosonic quantum field theory and slowly move towards a conformal field theory direction, because previously the ideas of complexity was also not investigated in the field theory direction. So it was not clear how the field theoretic complexity should behave at all. So that's what I'll be talking about in the next few lectures. And to begin with, in these studies, what interested people and what this study was basically started by Jefferson and Myers.
Aranya,
yeah.
Sorry, I have a question.
Yeah.
You said that, can you go back to the slide one? The slide before this, the one before this.
Okay.
So when you say Nielsen found that complexity grows with time even after thermalization, or what kind of thermalization was he speaking about? Is it the subsystem thermalization or?
No, so what he found that in a system out of equilibrium as well, you don't really, the complexity keeps growing for a longer time, and it doesn't necessarily take into thermalization into consideration. So it keeps growing linearly with time. So thermalization, actually, to be precise, thermalization doesn't play a role. And in the qubit picture, I think Pratik can talk more about this. But yeah, thermalization really doesn't play a role. But what he showed was that it keeps growing for linearly with time, and so it should, since that was the motivation that Susskind also had, that the complexity should grow with time. And what he suggested that this input was maybe more regarding Suskind's comments that this should grow even after when entanglement entropy saturates, what in case of holography you can observe. And that's why he suggested that the gravity duals that he suggested was indeed dual to complexity. But we have to be really sure about all of these things. What one needs is to investigate these things, or the notions of complexity in case of a field theory or a quantum field theory or a conformal field theory rather.
Sure.
Yeah.
Pratik has a comment.
Yeah.
Yes, so actually, as Binay asked, Nielsen work has nothing to do with this thermalization.
Yeah,
thing.
that's why
it is completely different. Nielsen works
that I'll be
that you can approximate unitary an unitary operation by d to the power cubic gates. D is the geodesic distance in this is some manifold. So there is nothing to do with this thermalization time, and this is purely from a Susskind point of view. Is Nielsen works?
But we can also talk about this later. But what I think is mentioned as the affine parameter in Nielsen's works is sort of analog of a time. So when you call the length of the geodesics, it also sort of reflects that the affine parameters, it's a power of affine parameter, and you could think it of as an analog of time, I would say. So it grows with time. That's output of the.
But Nielsen didn't talk about any thermalization. Nothing.
Yeah. That's what I told Vinay. That was probably input coming from our intuitions coming from Susskind and to match with his calculations. Yeah.
Okay.
So. Yeah. So finally, but what Jefferson Myers took. The ideas that Jefferson and Myers used in their work was motivated by the works that I and Pratik were talking about. So I'll just take a little bit more time, maybe 5 or 7 minutes, to discuss a little bit about Nielsen's work, which I
don't know, you can have 10 minutes extra.
Okay, thank you. So what Nielsen did was to consider if we have a psi initial and a psi final, then what he considered the problem from the point of view of a Hamiltonian control. Where you say that psi f, or the final state, is some time evolved state of you get from the initial state by acting it by some unitary or some time evolution. Where the Hamiltonian itself is time independent and you go from 0 to 1. So you could have two other way around. Previously, we were writing that the final state was some unitary into y, where this u is a collection of, say, C number of gates taken from our universal gate set. So what Nielsen does is he matches this two scenarios. One of them is dealing with the final state as a time evolved state, where the time evolution is done by a time dependent Hamiltonian, and the other is dealing with a combination of unitary gates. So and he problem boiled.
I don't know.
Yeah.
Abhishek is asking what is optimal Hamiltonian control.
Yeah, that is what I'm going to talk about. So that is when you have a time dependent Hamiltonian, what you want to do is that you want to, or rather what we are doing it by hand here is we are trying to think of the final state as a time evolved state of the initial state, and we want to track that what kind of time dependent Hamiltonian could give rise to such a final state in time 0 to 1. And then what you want to do is that you want to control your or you want to construct such a Hamiltonian, or you so that the number of gates is minimized in there. So you want to when we go on, you will see that we write the Hamiltonian in terms of the universal gate sets, gates that we want to use. And so we want to optimize the Hamiltonian in terms of the universal gates that we use. And that will be equivalent to saying that we are counting the unitaries present in this unitary operator. Or rather, yeah. So we want to.
I don't know. I have a question, sir.
Yeah.
in this case, when you are writing psi f is equal to u of psi I, are
Yeah.
you ignoring tolerance or is there
Yeah. I am ignoring tolerance. I am saying that, say for example, this psi f and this psi f has difference of epsilon, which we earlier talked about.
Okay.
Nishant has a question.
Right. So are there any assumptions involved, or you can always find some sort of a time evolution from initial to final state that would match your this U operator that you are applying in the second case? Like, will there always be a case that given the set of universal operators that you have applied, from going from initial to final state, you will get a corresponding time evolution from that state to a final
Like
state?
usually, when you are talking about if you are actually trying to look at a system where it is actually time evolving, and if you know the Hamiltonian, it's fine. Otherwise, if you can figure out the Hamiltonian, you can actually do this time evolution. But the way Nielsen approaches this problem is actually what I said in Orber's answer was also, I should rephrase, is since this U operator is also made of the gates that are present in the universal gate set, and the Hamiltonian that we have written here is a time dependent Hamiltonian, and we are going to write it in terms of the universal gate set is constant, right? So we want to write it multiplied. If we consider the universal gate set to be sigma I, then we would write the Hamiltonian as some control function which is indeed time dependent with multiplied by the elements taken from universal gate set, and therefore we want to also approximate the state from in both these lines. We are using the same universal gate sets, universal gates from the gate set, and therefore both of these are sort of approximated versions through which we are trying to reach to the final quantum state from the initial quantum state. There is, to be precise, there is a priori no such exact Hamiltonian, but since we are also constructing the Hamiltonian in terms of the universal gate set, we are actually modeling this problem in a way where we are sort of dealing with it as if we are introducing a Hamiltonian which indeed transforms the initial state to this final state. A priori, there is no such Hamiltonian in actually, but yeah, we are trying to model it again by using the same universal gates that are in this unitary. So this unitary, we would realize these to be equivalent.
Subbu, go ahead.
Aranya, so I have a question. So in this formalism, so do you do this for given psi I and psi f, or like is psi I fixed for all the psi f's? What is the picture?
So typically the psi f is what usually people, since again, let me come back to the story of holography. Since in holography, what people really can calculate is the complexity for ADS black holes or the difference of complexity between situations. But in while difference between two, in holography, you have a clearer picture of what the two states you have. In this approach of Nielsen, he arbitrarily takes, you can take arbitrary.
What I mean is, will your Hamiltonian change? Like if I have a different final state, or if I have a different initial state?
Yeah, of
like
course, your gamma t, since this time dependence will change, right?
It is so it is like, do you have it like for a given initial state for any final state? Like, do you have like some Hamiltonian, or like for every final state there will be a different?
For every final state, you would have different Hamiltonians, because your Hamiltonian has this control function which will be different for it's sort of again, this Hamiltonian problem will eventually boil down to a problem of finding a geodesic and a manifold of
But then is the reference same for different states? Suppose I have psi f1 and psi f2.
No, there is ambiguity.
The initial state, is it the same?
Yeah, you can start from some initial state and you can call what you want to consider is this unitary is taking you from initial state to final state, right? So in unitary, this unitary, you have several number of unitaries, and what you want to say, we have a metric on the space of the unitaries, then what we want to calculate is basically the distance between identity matrix and
I'm just asking, is psi I fixed? That is my question. For
no,
different
psi I in a priori is not fixed for different problems. It depends on the relative complexity you want to calculate.
Yeah, I'm just saying, given a problem for different final states, is the initial state fixed?
No, I don't think so. The reference state is also sort of arbitrary, because what you can calculate is again sort of the relative complexity between two states, and for example, the situations. The situations we will deal with later. For example, what this Jefferson-Myers paper deals with is complexity between harmonic oscillators. In that case, we will typically take the reference state to be a state where the oscillators are all decoupled from each other in the position basis itself. So typically you start from an unentangled state, but the more concrete notion is to have the relative complexity when you have both your both your final and initial states.
Okay, thanks.
Okay, so how does he do this? Let me talk a little bit about that, and then I'll finish. So as I was talking about, the other goal is to basically, since we are dealing with, let's say, we are dealing with an n-qubit situation where we have an initial state and a final state, then you'd have to deal with 2 to the power n cross 2 to the power n sort of unitary matrices. These will be the dimensions of the unitary matrices. And so we will deal with SU2 to the power n space, although actually the space that should be considered is any unitaries, U2 to the power n. But what in his problem, what Nielsen simplifies this, or rather he takes a simpler situation and deals with SU2 to the power n. And what we want to get is basically some notion of distance or metric in the space of unitaries, which is space of SU2 to the power n. And we want to have some desired properties that this metric satisfies and all that will come into later. But again, yeah, so as I was talking about, he models this time-dependent Hamiltonian, whatever Hamiltonian is going to take me to my final state starting from my initial state is through this gamma t sigma I, which is a function of t with some sigma i's, where these sigma i's are, since we are dealing with n qubit scenario, you could in principle show that in case of 2 qubit situation, all you need to generate the, or even a single qubit or 2 qubit situation, you would deal with basically Pauli matrices as your universal gate sets. And so the universal gates are used here, or you could always write the 2x2 matrices and 4x4 matrices that we dealt with in case of the 1 qubit and 2 qubit gates. You could represent it through the Pauli matrices. So what Nielsen considers the sigma i's to be are n-fold tensor product of Pauli matrices, which he calls generalized Pauli matrices. And say, for example, when you want to deal with only 2-qubit gates, then you would take this generalized Pauli matrices to be for the qubits that you want the gate to act on. In those cases, you will take Pauli matrices. In other scenarios, you will just take identity matrices. Other qubits will be acted by identity matrices, and these will act like Pauli matrices. So these should also work as universal gate structure or universal gate set, this generalized Pauli matrices, and you have defined some kind of control function, or which we don't know, which will be different for different final and initial states. But since we are dealing with a quantum mechanical situation, it has to follow certain conditions. So in general, this, since the sigma is at 2 to the power n cross 2 to the power n matrices, and the elements of SU2 to the power n. So the gamma t will have basically 4 to the power, will be a 4 to the power n minus 1 dimensional vector. And the subtracted one is due to this SUN condition, where you can get rid of a 1 coefficient by asking that the determinant is 1. And to correctly synthesize the unitary U that we talked about earlier, that we want to model this U as similar to some IHT dt situation going from 0 to 1. The boundary conditions then will be U at 0 equals the identity matrix, whereas U at 1 is your desired unitary. And to follow the mechanics, you could, since you could take these two to be equivalent, then you have the U has to follow, or rather the in a way the control functions has to follow this equation, which is minus IHT U. Given these boundary conditions, this has to follow this equation, which is simply a representation of Schrodinger's equation. And the goal, again, as I talked about, is to get to a metric definition, which sensible definition of metric defined on the space of SU2 to the power n, which is done by basically asking for a function. So everything about the circuit is stored in this. Yeah.
I just want to remind you that you're already 4 minutes over your 10 minutes extra time. So
okay, so
can you
I'll
wrap
just
up?
end in 1 minute. Yeah. 1 minute. Yeah. So everything about the circuit is stored in this control function, which talks about the circuit as well as which varies for different initial and final states. And therefore, you want to have a functional of this control function, which you want to minimize. Let's say this functional gives you a or some integration of this functional over this time 0 to 1 gives you some cost function rather, depending upon this gamma, which also depends upon gamma. And you want to minimize, you want to take the infimum rather. There can be infinitely many valid control functions for which you will get different cost values. So you take infimums over all of them, and that will give you the CFUT as infimum over all gammas, CF of gamma. So I'll talk about these things more in the next lecture. So let me end
I think your iPad once again kind of.
Oh shit.
Last part.
Yeah.
I think while you sort of set up your iPad screen,
Yeah.
I think we can start taking questions. Pratik actually has his hands raised. So maybe Pratik, you can go ahead, unmute yourself and...
Yeah, so when Subbu was asking about the initial and final state, I just want to mention, see this initial and final state business can be best realized by in the condensed matter system. For example, if you take a many body system and its ground state, so this is our target state, the final state. We want to reach that state. So we start from a product state which is very unentangled state, and want to add some gates that Aranya was mentioning, that GC minus 1. So we start from an unentangled state and want to reach a this many body ground state, which is highly entangled state. This also tells why we need an entangling gate, because starting from an unentangled state, you need to go to the entangled state. So in between, you have to introduce some entanglement by these gates. So that's why this entangling gates comes. I mean, the gate set you are acting has to be the entangling step. So this is also tells that which kind of final state you can take. So that can be also some simple harmonic oscillator state, some quantum mechanical ground state, or something like that.
Yeah,
So,
Pratik, I'm familiar with all this actually. I just wanted to ask if in this formalism he is going to discuss if in the initial state is fixed. That's
sorry,
all.
I couldn't
And
hear.
here, I mean, I'm familiar with all this. I just wanted to ask in the formalism he is going to do with this. Is the initial state fixed?
Sorry, I didn't hear.
Subbu, maybe you just reply to him in chat. I think Pavan, go ahead and ask your question.
Okay.
Yeah.
Sorry.
Pavan? Pavan, are you there? You can ask your question, please. Okay, I think while we are waiting on Pavan, maybe Vinay, you can go ahead and ask your question.
I just wanted to know how does this complexity compare with other measures like relative entropy, for instance, which also sort of measures the distance between two states.
Yeah. So
and are
regarding
there
this,
any studies done or for simple qubit systems as to how they compare with each other?
As to why they compare with each other, I don't think there has been some computations regarding these things. If I remember correctly, is relative entropy is in some way it's related to fidelity as well, right? And there has been some calculations regarding complexity of purification side that I know of in case of mixed states, where people study the complexity from the Fisher information matrix and all. But I'm not sure whether a good comparison between relative entropy or entanglement entropy and complexity has been done for this kind of situations.
Okay, Shubham, go ahead.
Yeah, would any one of you be explaining or elaborating this in the context of CFTs? Like
the CFT, there is to be precise, there are probably 2 or 3 papers which have till now talked about the CFT aspects of the theory. This even the quantum field theory or the scalar free scalar field theory or free fermionic field theory papers, those are like 2 years old only. So the CFT papers have come out last month. 2 or 3 CFT papers have come out in last 2 or 3 months. So I may briefly talk about that if I get some time in the 4th lecture. If in the 9th lecture there is some time left for each of us, then I'll briefly talk about the ideas there. But to do that also we need the developed ideas that I will talk about in case of free scalar QFT and all.
All right, thank you.
Okay, I think Pavan has rejoined. He probably got disconnected. Pavan, if you're online, you can unmute yourself and ask the question.
Yes, I wanted to ask, how did you get that? Can you explain again the part about gamma having 4 power n minus 1 dimension vector?
Okay, so just let me. So your all the matrices, unitary matrices that you have in your 2 to the power n plus r 2 to the power n plus 2 to the power n, right? So there are how, if you want to talk about the independent elements in all of them, in all of such matrices, are the number is 4 to the power n minus 1 in case of SU 2 to the power n. Is that fine? So
yes,
you want a control function attached to each of those independent elements of those matrices.
yes.
Okay, so I think we should now thank Aranya for this wonderful lecture. Please unmute yourself and clap.
Thank you.
Okay, so I will stop the recording for today now.